Good afternoon, ladies and gentlemen, distinguished guests, and our dedicated students. Welcome to the William Mong Distinguished Lecture Come Workshop 2025 to 2026, an event that celebrates innovation and collaboration in the engineering profession. I'm Zhang, a PhD student in the Department of Electrical and Electronic Engineering at Hong Kong U Engineering. I'm delighted to be the MC and part of today's inspiring lecture. Since its inception in 1991, the William Mong Distinguished Lecture Series has stood as a hallmark of the inspiration and excellence within the engineering community. This prestigious series pays tribute to Dr. William Mong, a visionary leader and the founder of the Zhang Group, whose pioneering spirit and unwavering dedication have driven remarkable advancement across science and industry. Over the decades, it has brought together renowned scholars and industry pioneers, fostering meaningful dialogue, inspiring innovation, and encouraging future collaborations. Their vision continues to flourish. This year, we are excited to introduce a new workshop series alongside the distinguished lecture, bringing together researchers from around the world and reinforcing HKU's position as a global hub for innovation and collaboration. Today's lecture unlocks the secrets of Halide perovskite, the wandering materials transforming solar energy tech through a captivating keynote and dynamic panel discussion with world-leading scientists, where groundbreaking ideas collide and the future of clean energy takes shape. We are delighted to welcome our distinguished keynote speaker, Professor Mercouri Kanatzidis from Northwestern University. Together with Professor Ho-Baillie from National University of Singapore. Professor Anita Ho-Baillie from the University of Sydney. Professor Zhang Qichun from City University of Hong Kong. And Professor Wallace Choy from the University of Hong Kong. Joining us for the panel discussion today, I can't wait to hear their insights. The discussion is sure to be an electrifying exchange of brilliant ideas. To kickstart the lecture, let us invite Professor David Srolovitz, Dean of Hong Kong U Engineering, to say a few words. Professor Srolovitz, please.
So first, it's a pleasure to welcome everybody here, old colleagues and friends from many places I've been before. It's also very nice to have such a good-sized group of graduate students, young researchers here. It's always a privilege to hear from leaders in the field. And I think with this workshop series, I think we have an opportunity to get multiple perspectives on the topic. So as was introduced a moment ago, this is part of the William Mong Distinguished Lecture Series. And it's we changed the format for those of you who've been around for a while, and now combine the distinguished lecture with a small workshop to try to magnify and build on the ideas. It's really interesting to hear about solar energy technologies, because it's one of those fields that seems to change so quickly, and there's a constant march upward in terms of efficiency. And I hope the current trends right now, where there seems to be renewed interest in more traditional forms of energy, I hope it doesn't distract too much from what's really important. So as a material scientist, I'm not surprised to see new materials driving technology development. You know, as a material scientist, we always think about materials as the enabler of all the other technologies. And I guess the synthesis side, the chemistry side, is the enabler of the materials part. So there's so much going on right now. The organic-inorganic layered perovskitoids are particularly interesting as an extension of the more classical halide perovskites. And, you know, was looking just recently at some of the literature and talking about how important they are for improving efficiency as well as stability. You hear a lot about efficiency. You hear less about stability issues. And without the stability, all the other properties are kind of purely academic. I mean, we are academics, but at the same time, we do have to care about all the other things. So it's my particular privilege to welcome our distinguished William Mong lecturer, Professor Mercouri Kanatzidis. So I could get the accent on the right syllable. He's the Charles E. and Emma H. Morrison Chair Professor and a Senior Scientist at Argonne National Laboratory. He's a well-known leader in the field of materials science, materials chemistry, and he's been honored by too many awards to list. So please forgive me for not going through the whole list. He was elected to the National Academy of Sciences, the AAAS, FRSC, as I mentioned, he's a leader in the field of halide perovskites for solar energy conversion, and with particular focus on a lot of the synthesis and semiconducting properties of materials. Usually, when I introduce these kinds of speakers, they're in fields too far away from my own for me to have more than pure general interest. But since this is so materials related, I'm really looking forward to hearing it on a personal level, not just as the dean. So let me not take too much more time and welcome Mercouri to tell us more about these fascinating class of materials. So thank you.
Thank you.
Do you have the wireless microphone?
Oh, yeah, sure.
Okay, well, thank you so much for this great honor. It's a great honor for me to be invited to the University of Hong Kong to give this distinguished lecture. And I've been thinking about what to talk about and at what level. Perovskites now are well known, and they're very exciting, not only for solar energy, but many other applications, including detection. And some of you may wonder, how did this field emerge? Where did it come from? Before 2012, no one knew about perovskites. So I'm going to tell you a story. How we got into this field and a little bit of its prehistory and how it evolved and what it is today. That's the how part of the title. So, but before, I want to tell you about my group. This is the latest photo at Northwestern. Mostly chemists and material scientists, and occasionally a couple of physicists. It's a very interdisciplinary group. All of them are not working on perovskites. We do other projects, and I'll tell you a little bit about some of the other projects. But they're all very motivated and hardworking and very smart. So I'm lucky in that, because without them, I wouldn't be here talking about it, talking about anything. So I was trained in synthesis. I'm an inorganic chemist, and I learned and got excited about how to make new things. Oh, full disclosure, Professor Zhang, former group member, in 2007, 8, before he went to Singapore. So he did tremendous work in my lab in synthesizing novel materials. So the core interest of mine is synthesis and synthesis science. How do we make the next material, the next new material, regardless of what the next new material is going to be good for? Basically, somebody has to learn how to make things as a methodology, as a science, not just to have a great solar cell material, to have a great detector, or a great this, or a great that. So we develop the science of that, and then occasionally we get lucky. We find a material because we measure properties. And when you measure properties, you're going to notice things. Like if some property is very enhanced compared to others, you notice that. So when that happens, we tend, the discovery tends to impact another area. So for example, 25 years ago, we discovered interesting materials that were thermoelectric candidates, and we basically resurrected a dead field back then, 25 years ago in thermoelectrics, because now people saw that new materials could be made with promising properties. And that became even bigger as a project in terms of funding and members than the core project. And so this happened a number of times. For example, we have discovered materials for nuclear remediation and the cleanup of wastewater from heavy metals from industry. Now we're looking for the most difficult problem in science, to discover new superconductors. We discovered X-ray and gamma ray detectors, and again, span off, and then the perovskites. And so here I am to talk about the perovskites. In the perovskite area, I collaborate with some of the best in the field. Ted Sargent is at Northwestern, and he's now my colleague. We co-supervise several students, for example, Isaiah and Taylor and Yi and Dr. Zhang. All of them are co-supervised with Ted. Aditya Mohide at Rice is a great collaborator. We do theoretical collaborations and studies with Zaki, Yvan, Claudine, Katan, and Michael Kepeneki, and this is all one group, actually, at the University of Rennes, Ramses Sadri, Richard Schaller, and a few others. Some of the former members have moved on to become faculty in these universities. So the perovskite is a big deal because of a number of things. One of them is the fact that they're very soluble. So they're soluble, you can dissolve them, and then you can cast them on a substrate, remove the solvent, and recover the structure with the original properties. This is a big deal because if you cannot do that, then you have an insoluble material. You cannot do the chemistry. Then it's not different than, say, silicon or cadmium telluride and all the other conventional solar cell technologies where historically chemists have not been important because they used physical techniques, and physicists and material scientists are better at physical techniques than chemists. So this is number one. That's necessary, but not sufficient. So you can make the multi-layers, which means chemists can go into the lab and start playing with this and making layers and therefore devices. So the barrier to entry for chemists becomes lower. That means now you can involve many more scientists than before, historically, for photovoltaic technologies. And this is the crystal structure. Well-known crystal structure is known from the oxides, and these are the halides, however. So the structure itself is an octahedron of metal surrounded by 6 ligands, which are then the octahedra share corners, and that creates a 3-dimensional structure, and it has a small void. And if the structure is negative, for example, in these formulas, lead is 2+, iodine is -1, so the whole thing is -1, so it requires charge balance, and so a small molecule can fit in the cage and balance the structure. The most important perovskites are these two, the lead and the tin-based. Okay, so that's one. So they have joined the third generation photovoltaic technologies. Over time, we had the first generation based on single crystalline materials, gallium arsenide and crystalline silicon, which is, of course, the most commercialized material with very high efficiencies. Then we have the second generation, the polycrystalline film technologies, such as cadmium telluride and copper indium gallium selenide, with very high, also commercialized, at least the cadmium telluride. And these are the ones where chemists historically have not played a big role because they are not soluble, so you require physical deposition methods. And then the third generation are the soluble ones. Perovskites are one, but dye-sensitized cells, organic photovoltaics, polymer-based, quantum dot-based materials. And these are also now competing very well with the efficiencies and promise low cost, at least the perovskites. So another thing that is really true, that materials do improve over time with sustained development and sustained support, but it takes a long time. So each of these lines is the efficiency of a particular material in a solar cell rising, but it takes decades, as you see, many decades. As I said, silicon, all the materials I mentioned are represented here. What stunned the world is the perovskites came up only in 2012 and very quickly reached efficiencies that the others took decades. So that was surprising. Why is that? So I have to give credit for the emergence of perovskites to Michael Grätzel. I don't know if you heard of this name or the Grätzel cell. He invented the so-called dye-sensitized solar cell in 1991. He's very famous. He comes to Hong Kong quite often, and Singapore and places like that, Korea. He published this paper in Nature, and it was an amazing device, totally unexpected device for a solar cell. It was made from chemistry, liquids and solutions and solution processing. And he took a film, a porous film of titanium dioxide, polycrystalline titanium dioxide film, and on it he attached a ruthenium inorganic complex that absorbs light, and it attached it by these carboxylates on the surface. And this is the spectrum of this material. So it absorbs some light, it's visible, like 560, here 350. It's not a lot, but it absorbs some light. And so when this gets excited, then the excited state pumps an electron into the TiO2 band structure. And then that one gets oxidized. The electron then can travel, which is miraculous in itself, going from nanoparticle to nanoparticle. This becomes oxidized. Now if you can reduce it, you recover it so you can absorb another photon. And then he used the iodide-triiodide couple dissolved in acetonitrile or DMF to actually reduce this material, make triiodide, take the triiodide to the other side, and then reduce it again and close the circuit. So this was transporting the whole, basically, to reduce that, and the titanium dioxide, the electron. Chemists were very impressed by this because it was working. And by 2011, it was up to 10%, 11%, which was, at that time, this was an impressive number. People were talking that if you can make it 13% or so, it would be commercialized, that kind of thing. But there was a problem. It was unstable. Because this is liquid, the solvent eventually takes this thing off the surface into the solution, and then it stops working. And also the solvent creates other problems with the layers, and it leaks out, and the stability was very poor. So by 2011, everyone was struggling and thinking very hard to make this a solid-state device. And so the most logical approach when you look at this, you say, okay, all I have to do is maybe keep this because this is doing the work, but replace the solvent with something, maybe a polymer that can dissolve an iodide salt, make an ionic polymer, it would be conducting and do the same job. That's what they were doing. It was, and this efficiency was dropping down to 1%, 2%. So it kind of like almost working, but it wasn't competing at all. Now, all right, pause. Remember that. We'll come back. Perovskites. The first report we can find on perovskite materials is 1893. It's by an American by the name of Wallace in Connecticut. And he synthesized these materials, analyzed them, and described them, wrote a paper in German, and he published it in this German journal. Germany was the chemistry powerhouse in those days. And if you wanted to have a high-impact journal paper, you had to send it to Germany. 16 pages, and look at that. This is from the paper. All of these compositions, cesium-lead chloride, cesium-lead bromide, cesium-lead iodide, these are the perovskites. Of course, it doesn't call them perovskites, because perovskite name is not known yet. And there's no X-ray diffraction because X-rays had just been discovered as a phenomenon. So it just says this is how you make them, and it's correct. The colors are correct and everything. Now, you skip a few decades, and then you have this other paper in Nature in 1958. And this is half a page paper. This is the whole paper, half a page, okay? No supplementary material. It's half a page, and you know, those papers back then, and even up to recently, they used to be called Letter to Nature. You published a letter to Nature, and it was a paper. Well, this was a letter to Nature. I am willing to bet that this single author, Muller, wrote it by hand, sent it to the editor in an envelope. The editor read it very quickly. He was impressed and published it. No referees, no anything. Now, and photoconductivity of cesium plumbo halides. Plumbo means lead. And because now we have X-rays in 1958, he says these crystals actually are perovskite structures, same as perovskite. And the most interesting thing is this part. It says they are photoconductive with a cesium lead chloride having its maximum spectral sensitivity in the violet, the bromide in the blue and green, and the iodide in the red. And he's describing the bandgap trends, becoming redder, okay? And yet, no one pays attention to this paper. Nobody, nothing. It's just published there. Zero, very few citations. But it was there. In 1978, another paper, Perovskites, 1978, by Weber. He describes now, he changed the cesium into methylammonium. And he describes a family here with chlorine, bromine, and iodine of perovskites. He lattice parameters and then the colors. These are the colors in German, but no properties or anything like that. And again, this paper goes unnoticed. It's just another compound. Chemists publish compounds all the time. This was another one. So these materials did not capture any attention. That's why I call them humble. These were humble materials. Nobody was impressed. They were disordered. They were made by sloppy techniques, by mixing things and then getting them precipitate. So this was the age of humble. In 2008, you were there. When did you live? In 8? Huh?
I'm still in your group.
Yeah.
I'm living there. Another 2008.
Yeah, okay. I get a call from someone in Palo Alto, California, who says, we want to talk to you. We are a startup company. Just started. We got some funding. We got about $5 million funding, and we have an idea to commercialize a novel solar cell. And I said, well, what is it? He says, well, it's not your standard photovoltaic cell. It's different. We want a material that will absorb solar light, so that means it should have a band gap of about 1.3 or more, like 1.3, 1.4, 1.5 electron volts, and then take that light and emit it from this band structure into one wavelength. And that wavelength should be about 950 nanometers. I said, why 950? He says, because that's right above the band gap of silicon. Silicon is about 1,000 nanometers, so 1,100 nanometers. That way, he says, if we have silicon and silicon absorbs that light, we would lose very little energy. And then silicon photovoltaic will convert the light with 95% efficiency into electricity. And so here's the design. This is the presumed film that would absorb the solar radiation. It will emit, but it's supposed to guide the light sideways, not back out. And then here's the gray, these are the gray, very thin silicon solar cell. Because it's very thin, it's going to be very cheap. So that's the low cost part. And said these will be the converters, and we have the technology to guide it sideways, but we don't have the material. And I said, okay, that sounds interesting. I never heard of this idea. Sounds interesting. Why are you calling me? And he said, well, you are known to make materials, new materials. You're synthetic chemist, and maybe you can help us find one, or maybe you already have one that would do this. And I said, how did you find me? And I said, from the internet. I said, what do you mean from the internet? We Googled you, and we found some hits, some sites that, that you're publishing many materials. There was probably some press releases, who knows. And I said, okay, well, I still don't understand exactly what you want, but they said, okay, we're going to come to Chicago, we're going to talk about it, and to show you that we are serious, we are willing to fund a postdoc in your group for a few years to make it happen. Oh, so in that case, I was interested before, but now I'm even more curious. So they get on a plane, they come to Chicago, and we spend the whole day, many hours, in my office. They showed me like 80 slides, maybe 120 slides or so. I still have them. These are two of the slides from that presentation. These are the OmniPV slides. And they explained everything. I got excited, but I said, I don't know if we can do this because I am not known. I'm known to make materials, that you're right, and I can even design the band gap, but I am not known how to design this wavelength that you want at 960. It has to be at room temperature. It has to be intense. And to my encyclopedic knowledge, nothing emits that strongly in the near infrared. Everything quenches. You have to cool it down to 77K. You want it at room temperature. I don't know if we can do it. So, okay, we set up the collaboration, and then I started going to the literature. I said, well, we need band gaps of 1.3 or 1.4 eV. I found some papers in these journals with these chalcopyrides, copper aluminum telluride. I found this paper, which at 78K has an intense peak at 1.1 eV. We wanted it a little bit bluer, but that's okay. But then the room temperature one was weaker. And then I found this paper, copper, aluminum, sulfur, selenium salt solution, and they could tune it. Oh, that's interesting. And this went up down to 710 nanometers. I wanted it here. We needed it here. I said, well, maybe with some chemical manipulation, we can bring this down there. So we went to the lab and made some of these compositions. This is our data. And this is the absorption spectrum. The band gaps are okay, a class of 1.3. And it doesn't have emission at room temperature at 1101, not exactly 950, but it's very ugly and it's very weak. So I was beginning to feel nervous whether we're going to do this, we'll be able to do this or not. So I went back and I found some papers from this scientist. This is, very few people know this scientist. His name is George Papavasiliou. a pioneer in quantum dots. Have you heard of him? A pioneer in quantum dots and perovskites. In the late 80s and early 90s, he was publishing perovskites already. Look at this. This is a 3D perovskite. This is a 2D perovskite, 1D perovskite, and even 0D. And I had met him in 1989 in a NATO symposium in Spetses, Greece, and we spoke, and that's how I remembered his work. And he was publishing in not very famous journals, and I found this paper, and this paper was like on perovskites. You see, these are organic-inorganic hybrid perovskites, synthetic metals. I find this, and these are a bunch of absorption spectra and emission spectra, and all of these compounds. And I noticed this thing here. And this is dotted line. I don't know why it's a dotted line, but it's 837, not quite what I want, but it is room temperature. And this is from this material, methylammonium tin iodide. That's a perovskite. So I said, you know, this is close enough. It's not what we want, but close enough. Let's make it and see. Maybe we can find a way to put it into the red. So we made it, but then the company said, no, this is not good because it has organics. And if it's organics, it's not going to be stable. You need to make it inorganic. So I put cesium in there. But very soon, I found this paper. 1993, Yamada et al. They are reporting the same material here. These are perovskites, cesium, methylammonium. And they say this is a metallic material. Metals don't emit. And this is very convincing. This is the conductivity versus temperature. And this methylammonium and cesium, these are the conductivities, and you cool it, and the conductivities are going up. That's the definition of a metal. Well, that's bad news. Then this is confirmed by another paper by David Midzi in these two journals. This one is a letter to Nature. And he says this material is actually metallic. And he shows this plot, methylammonium tin iodide, resistivity versus temperature. Look at that. It's falling. This is undeniable. So what the heck is going on? And then also, the two-dimensional ones, he even says, are metallic. Well, I said, this is confusing. Papavasiliou says they're semiconducting. They're saying they're metallic, and I cannot argue with this plot. So I said, we're going to do it ourselves. We're going to do it for ourselves and figure it out. We're going to solve the structure, make sure we have pure material, and understand it in great detail. So we did that. Eventually, we started in 2008. The paper came out in 2012. And indeed, this material is not a metal. It's a semiconductor. We made it pure, high quality. Here's the absorption spectrum here. This is, you see, the band gap is 1.3. And then look at the emission. But band gap emission 960, perfect. That's what we need to do. And it's actually room temperature and intense. But between 2008 and this paper, it wasn't always intense. We had problems. It was not reproducible. Sometimes it was weak. Sometimes it was strong. We were very confused. Okay, then how do I explain the metallic behavior? Well, let's measure the conductivity. This is conductivity versus temperature. The pure sample, the high quality fresh sample, is very low conductivity. But if you measure this in air and you heat and cool, and heat and cool, the conductivity goes up. And now this is the undeniable curve that is metallic. So what's happening here? We take an X-ray diffraction. It's not decomposing. It's the perovskite. And what's happening is it's being doped. Some of the tin 2+ is being oxidized to 3+, and introduces holes into the material, lots of holes. And now you have a partially empty valence band and behaves like a metal. Now we also measure the Seebeck coefficient, which is a measure of if we have N-type or P-type. If it's positive, you have holes. If it's negative, it's electrons. Clearly, this is positive. And the more holes you have, the lower the Seebeck. And the same thing happens here. You have high Seebeck with very few holes, and then you cool and heat in air, and this is what happens. So the air dopes the material. Now that we understood this, we knew we can have it both ways. We can have a conductor if we wanted it. We can have a semiconductor if we wanted it. All right, so back to 2008, Zhang was playing around to try to reproduce and make it reproducible and robust and maximize the efficiency. So here's some from his notebook, some of the compositions he was playing with in this page. Cesium tin iodide chloride, cesium tin iodide, different stoichiometries. This is the band gap he was getting. So that's a good band gap. And these are the emissions, 960, 961. If you put a little bit of chloride, it goes into the blue. And these are all in the right place, room temperature. And it was great. So we were very excited. We told the company, we solved your problem. This is by now, it's like 2011, end of 2010. Here it is. We were also learned how to make films, which they wanted films on rigid substrates, flexible substrates. The films were very nice and emissive and so on. All right. Now, in end of 2010, I get a message from the company and says, bad news, we are closing down. And the reason is the investors are not willing to put any more money. And a few other reasons that you don't have to worry about. Like I said, it wasn't us, right? It's not because of us. I said, no, you have nothing to do with it. You did what you're supposed to do, what you promised. But we're having financial problems, we have to close down. By that time, we had amassed a vast amount of information on the perovskites because we didn't only study the tin. We studied the lead. We studied the bromide. We studied the methylammonium, the formamidinium, the cesium, everything. We solved the crystal structures precisely. We figured out the phase transitions as a function of temperature. We measured PL from everything. We measured solubility properties, band gaps, you name it. So all this information just to understand this material. Because, as I said, we were having strange things happening with this. I said, okay, now we have to go back and study the whole family to see the trends. And that helped. I asked them, what are we going to do? What do you want us to do with all this stuff that we have? They say, it's all yours. We're not interested anymore. We're going to close down. You can keep it. You can publish it. You can patent it, whatever. Okay. Now, I have a big job to do to write all these things up. And then here comes Bob Zhang. And at Northwestern, we have a nice tradition in the department. Every Tuesday, we have lunch, the faculty. The faculty get in a nice small conference room, about 25, 30 of us. And one of us has agreed to present a talk, about 40-minute talk about their research. And the rest of us are eating lunch. And so that's how we find out what everybody else is doing in the department. And this talk actually often nucleates or stimulates collaborations because you hear what the problems they're having and you try to help, and vice versa. So Bob came in, and Bob Zhang from Hong Kong, I think. He was from Hong Kong. He passed away. He was much older than me. And he had worked at Bell Labs, and then he came to Northwestern. He was president of the MRS for a while. He was working on dye-sensitized cells, and he was trying to make it solid. As I said, back to Gretzel. He was trying to make it solid. And he was trying to do it the intuitive way, to make ionic conductors with polymers, with the iodides, and he was making the devices. And all through 40 minutes, he was complaining how the Grätzel cell has to be fixed, it has to become a solid, and he was showing his results. And his efficiencies were 2%, 3%. And that's the first time I heard a good Grätzel cell talk, because every other time I heard it was all electrochemistry and interfacial electron transfers and stuff that I wasn't interested. And I understood what he was saying. So after the talk, I went to him and I said, you know, Bob, if I understood you correctly, you want to make a solid-state cell, and you are looking for something to take the hole out of the cell, right? And you want to do the iodide-triiodide couple, like Grätzel does. He says, yes. Well, I said, how about, like, if we had a material that was p-type and was solution processable, and we throw away all the salts and deposit that, could that work? He says, yeah, it's an interesting idea. Let's try it. So we decided to try it, the two of us. My postdoc in Zhang, my student in Zhang, and his student, Byung-Hong Lee. So they went to the lab, and after about a month, they want to talk to us. We have a meeting in my office, and Bob is late, so we start. So he was late by 15, 20 minutes. We start. And they're showing me these results. This is directly from the in Zhang's notebook. And he showed me this plot, and then showed me these parameters from this device, and the VOC is like 0.2 volts, and I go directly to these numbers because I'm going directly for the throat. And this number is like 0.078. And this one is 0.2 efficiency. So, okay, so much for the idea. It's not working. And then Bob comes to the meeting. And now we have to repeat everything. So Bob sees this, and he says, you know, it's working. The idea is working. I said, what do you mean? He says, well, I like, first of all, I like these curves. And the reason this is low is because the device is lousy, it's not well made. They don't know how to make it. Let's talk about how to process. Tell us more about the material, and we'll make improvements. So we sat there, gave him some instructions on how to make a better device. After a month or so, another meeting. Now they're showing us basically similar plots, and the efficiencies are a little bit better, 3.1, 3.0, and 1.6. I'm still not impressed, because already these efficiencies have been achieved with the conventional approach. But again, Bob is encouraging. He says, you know, this is working. See, it's better, but it can get much better. All right. So they went back, and they were coming back and forth, back and forth. Every month we were having a meeting, and the efficiencies were going up 1% a month. And it's like a stock in the stock market. It was going up 1% a month. After 8-9 months, now these are from the notebook of In Zhang. Look at this. Now we are June 9, 2011, and we have this beautiful looking device, and now these numbers are 7.78, and 7.3, and 9.7, and so on. And now we're talking. Now I'm getting excited. And this is the magnification, 7.78, 9.74, and so on, 8.23. All right, it's working. We improved on that, and he also on the June 13th, I noticed this in his book. He drew this by hand. This is the absorption spectra. This is the absorption spectra, comparing the dye-sensitized absorption of light and our cell absorption of light. And our cell, he says, is absorbing to the red. So, you know, it's working not because the dye is there, because the perovskite is there. The dye cannot compete for absorption because this is the band gap is 1.3 eV, and the dye, if you can talk about a band gap, it's about 1.8, 1.7. So actually here. So here's where the perovskite is absorbing already at 900 nanometers. That's the film. That's the device, the film. The molecule is absorbing at 650. So a molecule is absorbing here, the perovskite here. The dye is not doing anything. It's the perovskite acting as an absorber and at the same time as a whole transport layer. Remember, we can have it both ways because near the TiO2 is actually good. It's a semiconductor. But as it goes up during fabrication, it gets a little bit doped. It becomes P-type, and that's where the electrode is. So it's doing both jobs. And therefore, so we wrote it up, and we published this paper. And this came out in May 26, 2012. This is the first paper of a perovskite solid-state solar cell that was published. It was, we submitted it February 6, accepted in March, and it was published in May. And this is the spectra we put in there. This is absorption spectra. The black is just a standard Grätzel cell. And here's our spectra. You see the redshift. Also, the EQE spectra shows excess efficiency because of the perovskite contributing to the performance. And so this came out, we filed the patent in February 21. So it made a big impression. People noticed, they were excited about it. Efficiency was 10%. And then a few months later, 2 other papers came out, several months later. So on October 4, Henry Snaith published this paper in Science using a lead perovskite. Remember, we also studied the lead perovskites. He's used the lead perovskite. This is the Weber compound in 1978. This is now 11%. And then in August 21, Namgyu Park from Korea published this paper in Scientific Report, very similar to the Snaith paper, with 9%. And these papers were actually submitted after we published. So they cite our work. They saw our work, they cite our work. And these 3 papers are basically the 3 papers that captured the attention of the Grätzel cell community first, and then many of them started working on the perovskites, and then many other communities that came in. So that sparked the photovoltaic field. What about all the other knowledge that we had that the company said you can have it and you can publish it all you want? So we published it in this paper, all the compounds. This is a long paper, and it has all the analogs here. In this paper, actually this paper was first submitted to JACS, Journal of the American Chemical Society, and it was rejected because they told us it was going to be not broad enough interest. It doesn't quite rise to the level of JACS because it's not a broad enough interest. We had 2 negative reviewers and 1 positive reviewer. So we sent it to inorganic chemistry. It ended up being, by now, the most downloaded, most read, and most cited paper in the history of inorganic chemistry. The editors told me this. Now, in this paper, we have many compounds and precise crystallographic determinations. I emphasize that. Why? Because there's a supplementary material that's even longer than the paper. The paper, all the experimentalists who were coming to the field to learn how to make perovskites, they say, what are these perovskites? We want to learn more about it. What do they look like? How do you make them? What are the properties? They found this paper, and that's why it's so successful, they all read this paper to start their work in making devices. And in this paper, for the first time, we published formamidinium lead iodide. This was not known at the time. It was a new compound, formamidinium lead iodide. And these are all the analogs now. All perovskite with lead, for methylammonium, formamidinium, and cesium. And you see, this is emission, and the light of formamidinium is more red, and then it's MAPI, and then this reflects the band gaps. So the band gap of formamidinium is less than MAPI. And here's the absorption, and here, of course, is lead and tin. But again, this is the spectrum of the formamidinium, which is 1.48, whereas MAPI is 1.55. And people notice this, say, "Wow, what is this? This absorbs a little bit more light. Maybe we should use this." And now all the top perovskite solar cells that break efficiencies, reaching 26, 26.5, 27, they're based on this material with a little bit of doping with other cations. Also, in this same paper, we also discovered and published something else which became important later. And that is the band gaps. These are, again, the absorptions, and these are the band gaps. And what we have here is tin band gap, which is black. This is this one. The tin band gap is lower than the lead band gap in methylammonium, as you can see here. But when you mix lead and tin, the mixed ones are even lower than the tin. So now you have even more lower band gap. We demonstrated that this can actually be used in solar cells, so you can capture more light in the infrared. And this is our paper in 2014, showing that actually when you have mixed lead and tin, you can push it. You can push the absorption into these numbers in the infrared. This became now the foundation of tandem cells, because in tandems, if you want to get 35, 40, even 50% efficiencies, the future direction of perovskites is tandems. You need to have two cells, maybe even three. A wide gap perovskite that captures part of the light, the rest of it goes through. A narrow gap captures the rest of the light. And together, the efficiency is much higher. It's the way to 35 and 40%. But you need this narrow gap bottom perovskite, and you can make it narrow by mixing lead and tin. So this became also a key discovery. All right, so now we have 2013. We have to now start. Let's go to some meetings and tell people about it. The paper is out. There was a symposium B, Organic and Hybrid Photovoltaic Materials and Devices. This date, 2013, in MRS. We sent the abstract in there. And we sent it in December. About February, we get an email from the MRS, from the organizers. And they say, our abstract is rejected. Why is it rejected? Because they say this is irrelevant. These are not interesting materials. They're irrelevant to our symposium, because their symposium was more on organic PV and polycrystalline, copper indium selenide and cadmium telluride. And they could not, even though the paper was published, it still was not well known, even to the photovoltaic community, the classical photovoltaic community. So they get our abstracts rejected. How many abstracts of you have been rejected in your career? Who gets his abstract rejected? This never happened before or since. This is the one time. So this is sort of that captures the development of the field. Where I say, before 2012, this is the age of humble. Nobody cares. The materials are known, but they are not important materials. After 2012, with these three papers, now it's like the age of heroes. The heroes are coming in, and they are pushing efficiency by leaps and bounds. They went to 14%, then went to 15, 16, 17. It was like dizzying rise, and now we are close to 27%. Now, of course, we're going to get another phase, which will be the commercialization and the reality of stability and all that is going to come through. So it needs to be solved. What the iodides, the lead perovskites, tin perovskites did to the PV field, the bromides actually impacted another field on X-ray detection and gamma ray detection. And this, again, we published this in 2013. For the first time, we claim that the cesium-lead bromide perovskite, bigger band gap, red material, can actually detect X-rays and gamma rays. And we published this in this paper, and the same experience, very much resistance. Zhang also rejected this paper. And this, again, is the highest cited paper in crystal growth and design. Not as highly cited as the previous one, because this field is a little bit smaller, but it is a high in this journal. So we report that. This is a subfield on its own. I'm also working on it for X-ray, developing X-ray imaging and gamma ray detectors, like here. Unlike films, here you have to grow very big crystals for gammas. And so we're growing using the Bridgman method, many centimeters long crystals that we can cut and using devices for hard X-rays and hard radiation detection for a number of applications. But I don't have time to talk about that. So we have a big industry developed on the PV, more than 200 companies. These are just you can pull out from the internet at random. This is important. I had a relationship with this company, Oxford PV. This is Snaith's company, and I think they're the most advanced in terms of pushing it into the market. But others are close as well. Okay, now let's talk a little bit about some science. Why do they work? These things are not supposed to work. The supplementary material had all the crystallographic coordinates in that paper of inorganic chemistry. All the theorists of the day were looking for crystallographic coordinates to do calculations because they were doing models. They were making up models in the computer to calculate. They didn't have actual real coordinates. All the early calculations and then some were all those data were obtained from that supplementary material to do the calculations. All right, back to this. The bonding in an octahedron, this is freshman chemistry now. If you have a lead that is lone pairs, it's 2+, it has a lone pair of electrons in the s orbital, the p orbitals are empty, and the halides are full. It's X minus, like bromide, iodide. To stabilize this octahedron, you have two interactions. One is this between the field 6s and the p orbitals of halides. But this is not really a good interaction because everything is filled, because this is full of electrons, this is full of electrons, this is full of electrons. This is antibonding, bonding. But you don't get stabilization because the antibonding is also filled. Stabilization comes from this interaction where this is empty, they interact, these electrons form this band, energy goes down, antibonding is empty, goes up, and you have a stable compound. However, the highest occupied state is this because of these electrons, and the lowest unoccupied state is this. So this is the HOMO-LUMO gap, and this is the band gap too. If this becomes a solid here, this would be the top of the valence band, and this would be the bottom of the conduction band. And that's important. And now, what does that, why is this important? This is just cartoons of band structures of conventional semiconductors like silicon and perovskite. They look very similar. There's a conduction band and there's a valence band. However, in this bonding arrangement, silicon, germanium, gallium arsenide, cadmium telluride, this is bonding. So if you take, if you have a defect here, like a vacancy or an anti-site defect or something else, a state comes off and moves into the gap here. And the same here. If you have some kind of defect, an impurity, a state comes off and comes into the gap. These are trap states. If you excite electrons and holes, these things are likely to be trapped very easily. So to get these things to work well, you need to work very hard to remove these states. So crystal quality has to be exceedingly high. The impurity has to be exceedingly high. That's why silicon has to be like 9/9 purity to get this to work. And if you can achieve that, it's fine. It works. But it's hard work and can get expensive. So it's unforgiving to defects. The perovskite, when you have the similar defects, these states, they don't go into the band gap. They go into inside. Why? Because given that this is antibonding, anything away from that, it will make it bonding. So if it's bonding, it will come down. So the defect removes antibonding states, and therefore the state goes inside this band. If it's inside the band, it's not a trap. So this is defect tolerant, and this is defect intolerant. Now, that means that you can have this lousy lattice, and you can still get it to work because of this defect tolerance. And so right now we have 26%. The bulk lattice, because it's defect tolerant, can give you by itself 20% or 21%. However, the surface has defects like vacancies and other ligands here. Those can get into the gap on the surface. And so recombination happens here and you lose things. If you want to get the extra percent from 20, 21 to 25, 26, 27, you need to fix the surface. So the heavy lifting is still being done by the defect-tolerant lattice, but the extra has to be obtained by fixing the surface. And that's why these things were not supposed to work. Nobody was excited because they were disordered. They were dynamic and disordered, but they do work. So here's my analogy. The conventional defect-intolerant semiconductors are like this. You have a highway. This is the band. This is the conduction band and the valence band and the holes and electrons moving in opposite directions. If you have few carriers, you can move even faster. You have high mobility. You have to have a perfect highway. This is like silicon, cadmium telluride. If, however, this highway develops holes, big holes like that, and you fall, one of these carriers falls into one of these, you're stuck. You're not going anywhere. Now, the next hole could be over here. So between the holes, it could be perfect, but the existence of a hole is going to prevent you from going there. That means that your device is dead. The perovskites have shallow traps, or almost no traps. So this is the perovskite. The highway looks lousy. So mobility actually is not very high. Mobility of perovskite is 20 times, maybe even 50 times lower than silicon. So you're not going very fast. But the traps, these are not traps. They're very shallow. You have to drive carefully, but you're going to get there. Okay? So that's the difference between the two. Another thing is when you excite carriers across the gap, in perovskites, they live a long time, surprisingly long time, hundreds of nanoseconds. Why? In most materials, like few nanoseconds, maybe picoseconds, and they recombine. Well, this is how I view it. Lead 2 plus and tin 2 plus have lone pair of electrons. I already talked about that. There's two valence electrons that's still there on the atom. And these valence electrons require space. In other words, they are stereochemically active. This is why, for example, oxygen has two of these lone pairs, and that's why water is bent. And ammonia, nitrogen has one, And that's why ammonia is bent. It's not flat. Same thing here. So it wants its own space. It's stereochemically active. What happens here? Don't they want their own space? They do. But if you look at the crystal structure, it's perfect. It's like perfect octahedron. And so I said, no, this doesn't sit well. Why is it perfect? What happened to the lone pair? And so we said, we need to find another technique that is more local to see the local structure. So there is such a technique. It's called pair distribution function analysis. It's like powder diffraction, but instead of only taking into account the Bragg peaks, you take into account the total scattering, the diffuse scattering, and you analyze all that. And when you do that, then you can find defects that deviate from the periodicity. To fit this data, you need to move the metal atom off-center. Now, you don't see that in crystallography because it's dynamic and it's going in all directions. So it averages out into the center, but the real position is never in the center. And in tin, we quantify 0.1 angstrom away from the center. In lead, is about 0.08 angstroms. But it's dynamic, okay? And this is increasing. It gets even more as you heat it up. So why is that now? What's happening here? So we have this picture. It's a simplistic picture because some of these other atoms as well are moving, but this is what initiates this process. It never settles. It's a fight between the crystallography, who requires high symmetry, and the chemistry, which requires low symmetry. And nobody wins. And so you have this eternal situation. That means then, if this is dynamic and fluctuates, the electronic structure fluctuates. No electronic structure fluctuates. In silicon, that doesn't happen. It's rigid. So what is again, normally this would be bad news, because dynamic things, everybody likes things quiet and working. So here's my idea that if you excite electrons all across this gap, within a few picoseconds, the lattice is different because of it has changed. Within a few picoseconds, the electronic structure is different. They're trying to recombine naturally. They're trying to find each other. But because the electronic structure is slightly different, it takes them a while to find themselves. And it delays recombination. That lengthens the lifetime to the hundreds of nanoseconds. That means they live long enough to collect them. They move around in the field. They have long diffusion lengths. They don't recombine. You can recollect them. And this is also significant. How am I doing? Almost done? Huh? Done. Okay. All right. Good. I don't want to bore you anymore, but I decided to tell you the story and how these things work at a more fundamental level in simple terms, so you can appreciate these materials a little bit more and know where they come from. There's a lot more to say, but in the interest of time and respect out of the other speakers, I will stop here and be happy to answer any questions.
Thank you, Professor Kanatzidis, for that inspiring and thought-provoking presentation. And now, maybe invite Professor Srolovitz to the stage and present a small token of appreciation to Professor Kanatzidis on behalf of the faculty. Yeah.
Photo opportunity.
Okay.
This is Asia. We always have photo opportunity.
Okay, great.
They're very nice. And I love your picture with the roof and
Thank you very much.
For you. So you got the band gap?
Yes. Thank you.
Let's also invite Professor Wallace Choy, the host of today's lecture, together with all our panelists, to join us on the stage for one more photo.
This is great. Thank you.
Oh, wonderful. I especially like your Bangkok description.
I see.
Thank you. Next, we will move to our workshop session, where a group of esteemed experts will share their insights on the latest development and future directions in electrical and electronic engineering. I'm pleased to invite Professor Wallace Choy to introduce our panelists. Professor Choy, please.
First of all, I have to thank you all colleagues, particularly students, to join us today for this wonderful gathering with some well-known experts from the world to join us for this. Although it's just afternoon, but we are really truly international from different parts of the world. So I keep time short because I bit overrun. So we move to the next professor from National University of Singapore, Professor Hao. So I guess I don't need to introduce him in details, because if you just type down, even don't type down the university, Hao Yi, Perovskite, you can list out all his wonderful work in these last couple of years. So without further delays, I will welcome Professor Hao Yi to give us a wonderful talk.
I think this is fun, yeah. Just one. It's a laser?
Yeah, we don't have a laser, just a keyboard.
Okay, yeah. Okay, so thank you everyone. Yeah, it's a great pleasure to give a talk in Hong Kong, yeah. Yeah, I've been to Hong Kong several times, and actually, maybe 6 years ago, there's like kind of like a forum or workshop in Hong Kong U for recruiting the new faculty. Actually, I was also there. Yeah, long time ago. And yeah, great to get back to Hong Kong and to share our recent result in the perovskite tandem solar cells. And okay, so today I'm going to talk about how to unlock the potential of the perovskite solar cells from the single junction to tandem. Yeah, currently I'm the PYP professor at the National University of Singapore. I'm also leading the perovskite research at the Solar Energy Research Institute of Singapore. In short, we call it CIRRUS. And yeah, so background, I will go through quickly because I think Mercouri already did a wonderful introduction of the perovskite and the background, very comprehensive already. I will not evaluate too much, but I will give some motivation why we need to pursue high efficiency and stable solar technologies. And so if you look at in the past 7-8 years, and the solar energy definitely is a fast-growing one compared with wind and hydro. Solar is a faster one, yeah. And by prediction, and people believe in 2027, most of the places on the Earth will have the solar as the cheapest energy resources. So it's not renewable. It's compared with the core and all the things together. So definitely, I mean, we believe solar is unstoppable. Yeah, it's about the time.
Also
and so, if we want to accelerate the deployment of this solar technology, we need to look at the solar cell system cost breakdown. And if you look at the cost right now, the solar panel is about 25% of the total cost. So it depends on where you are. If you are in America, in Europe, and this number can be even lower, and because all the other labor cost and the land cost, and takes more, and it's more expensive. So that means if we need to make the solar cell more efficient, then we can dramatically lower down this 75% cost. So, okay, that's why the whole industry, photovoltaic industry, is pursuing this efficiency. The silicon start from the 5 years ago. This the PERC, developed by Martin Green at USW, and then the TOPCon. Right now, the TOPCon is dominating the market, and people believe the next generation it can be the back contact cell, the BC cell, and in between there's a heater junction. Yeah. Yeah, let's see. And yeah, because right now the space data center, the Elon Musk, talk about this a lot. And in the space, heater junction may find a very good application. But to be honest, in this territory, on this application on Earth, heater junction is very, very difficult in terms of the cost and the efficiency and everything. Yeah. So, but anyway, I just want to let you know. And so the industry involvement is actually driven by this solar cell efficiency. Yeah. And So if you look at this chart, you can see we have the perovskite single junction and the silicon single junction. Actually, both of them reach to this 27% region. So efficiency-wise, it's quite comparable. And but I mean, in single junction, we want to break this so-called SQ limit, and we make the tandem. Tandem, we put the perovskite on top of the silicon. You can see right now it's not updated. Actually, it's a 35 already. Yeah, recently it's announced by Longji. Yeah, and so it's a 35%. And if you look compare with the best solar cell materials, normally we say it's a 35 semiconductor gallium arsenide, and the perovskite silicon is already more efficient than this gallium arsenide. So yeah, obviously we need to make the tandem to accelerate the deployment of this solar cell technology in future. And but there's several challenges in making the efficient perovskite on top of this silicon for the tandem. And so if you look at this, you can see two big challenges here. And one is normally when we make the in the lab, yeah, and we make the small area solar cells, we use this so-called float zone wafer. Actually, this wafer is for the semiconducting industry. It's for the transistors, for chips. And it's very expensive, as you can see, it's more than $6 per piece. And for the solar cell industry, no one uses silicon wafer. Everyone uses CZ wafer. CZ wafer is very cheap. That's the one you see outdoor, this on the solar panel on your residential rooftop. It's using this CZ wafer. But the big challenge is if you use a CZ wafer, it's a very rough wafer compared with this atom flight float zone wafer. So you need to, to figure out how to deposit high quality perovskite on this very rough surface and to get a very efficient and stable perovskite silicon tandem and in large scale. Yeah, so at the very beginning, and we work on this perovskite silicon actually in 2018. And the paper was published in 2020. And so when we work on this, we noticed that there were some pioneers before us, like the Chris Balif at the EPFL and the CSEN. And they are the first one to demonstrate, double-side textured perovskite silicon tandem. And also Mac McGehee and Steve Albrecht, they have this, flat surface perovskite silicon. And so we think about, okay, and can we, make the silicon pyramid smaller in the range of 1 to 3 micron? How to use this one? Let me check. Yeah. Okay. Anyway, so if we use at the beginning we use this so-called 1, 2, 3 micron size pyramids, and we can demonstrate this is the Chris Balif group. They demonstrate this this double textured perovskite silicon tandem. So at that time we can we just reduce the pyramids to 700 nanometer, and actually it's feasible. And in that case we need to make the perovskite thicker. And we demonstrate, we can just make the solution process perovskite on top of this textured industrial silicon. And right now, if you look at this technology, and it's a solution processing, and the current record efficiency actually is based on this approach, and 35%. And with this, conformal growth, double texture is about 32%. So it's a more efficient technology, but it's not everything, because we find the stability is still a big issue for this. And quite recently, we developed this evaporated perovskite solar cells. And so the first, as you can see, and by evaporation, the perovskite film is very, very smooth. Yeah, the film is very, very, it's like a mirror smooth. And normally, if we deposit perovskite using solution processing, you can see something like this. You can see a lot of, small green boundaries, a lot of, voids or something as this barrier interfaces. And so this all triggers the degradation, of the perovskite. So you can see it's a very dense, very flat, very orientated perovskite. And if you look at the XRD, it's very, very pure also. And all you can see is a 100 and the 200 orientation. And the 110 is very, very small. So if you look at the ratio, is 252 to 1. And if you look at the XRD intensity, is 10 to 5, and the control normally is like 10 to 3. So the enhancement of this peak intensity is now 20-30%. It's 2 orders of magnitude better. And if you not look at this normal solution process one, you see many different orientations. If you look at the pole figures, and you can see dramatic in this contrast, and all this oriented perovskite centralized here and in center, but the solution process one because different orientation, and so it's different directions. I don't want to say this is a single crystal. Obviously, this is not a single crystal. This is polycrystalline, but the film quality is very high and shows some behavior close to the single crystal, but it's definitely not a single crystal. And so if you look at the stability and the Halide and the TM measurement, and then we can check the perovskite, the control device. And if you look at this, it's a tetragonal phase. And but if aged for a very long time and under this 110 degrees C, and you can see after quite a long time, it's become a hexagonal phase, which is lead iodide. It indicates perovskite is degrade. But with our this fully evaporated film, you can see after this long time aging, and the perovskite can still maintain this tetragonal phase. And yeah, so this solar cell is so okay efficiency because the wide band gap one. Its band gap is around 1.7. Its target is to match the silicon for in the tandem structure. So therefore, efficiency is around 21. It's not as efficient as the solution process, which is currently more than 23. Yeah, some group even report 24 already. But we just see the advantage of this one actually is okay efficiency, but the stability we see is much improved. And so this is the stability result if we age them at 65 degrees C, 85 degrees C, even 110 degrees C, and then we can do this, accelerated aging test. And yeah, so it's give us the confidence to make a conformal growth perovskite and onto the silicon. And that's the kind of the baseline. We know how to, evaporate stable, okay efficiency, perovskite, wide band gap perovskite, and the next step is we need to figure out how to deposit this perovskite on top of this very rough silicon, because silicon not only this soil damage kills the roughness, but also the pyramid itself give you this inhomogeneity of the deposition. And here you can see when we evaporate this, we use the three sources, yeah, FAI, lead iodide, and cesium bromide, and actually they have a different absorption energy of each component on this substrate. What we realize is, this organic component, FAI, is less easy to absorb on the substrate, and the inorganic one is easier. So it creates this imbalance of the absorption on the substrate. And this geometry of the pyramids make it even worse. And because this pyramid is peak, and this base position is also very different. So we want to solve this imbalanced absorption of the perovskite vapor on the substrate. And what we did is we modified the surface with this the silane group, this small molecules. And this is a typical silane group, and this part can attach with this ITO and the metal oxide. And then you have the functional group. So it's very similar to this self-assembled monolayer, but the anchoring group is now switched to this the silane group. Yeah, previously we used phosphonic acid, and but the functional group just help us to adjust this imbalance of the absorption. Here is just our DFT simulation. We can see how we can, using this structure to balance this. This is the inorganic lead component. This is organic, and before you see the very big gap in this binding energy, and about in the end we can have to find this balance with these molecules. So with the balanced this absorption using this molecule, you can see this evaporation at the very beginning, and the controlled samples without any modification of the surface. You can see at the very beginning of the perovskite evaporation, all you see is a lot of this inorganic lead iodide component. You don't have the perovskite forms. So with the treatment, you can see here, you can see more perovskite film peak formation, and so it's strongly indicate we can balance the inorganic organic component on the substrate to form a high quality perovskite. And yeah, this EDX also can tell us the nitrogen and the lead ratio. Nitrogen represents the FAI, yeah, and so it can also give you the ratio of the organic and the inorganic, yeah, and you can see it's you have a better ratio here. And this is our this Halide this TM, and the result you can see here. And we check different spots, yeah, from the horizontal Z direction 1, 2, 3, and also this interfaces 4, 5, 6 each spot. And without this modification, you can see we can have a lot of just inorganic lead iodide formation. But with treatment here, you can see we can get a very high quality perovskite at different positions. So it's very homogeneous. So this is the evaporated perovskite on this industrial silicon. And the performance is around 30-31%. And it was very homogeneous. We put it at a different spot at this 18 by 18 cm area, and you can see very close performance. And so because it's a conformal growth of perovskite on the pyramids, so you can see the reflection is very small, and the EQE response actually is very good. Yeah, so we did this stability, reliability test. And normally for tandem, stability it was challenging because you need to find a good light source. Yeah, because otherwise you're going to have a lot of current mismatch, many other issues. You can have the perovskite response, but silicon is not activated, and many other issues. So we choose a very good light source. It's LED based, and so we just light source can last for a very long time, because for the stability measurement normally it's about thousands hours. Yeah, so you need to operate this high quality light source for a very long time, and so this gives us this quite good stability, and especially this we basically tested two conditions. One is room temperature MPP, and this quite okay T90 is around 2,000 hours. Another one actually is this one, and which is 85 degrees MPP, which is a very challenging one previously for the perovskite silicon tandem. And here we can achieve T90 and more than 1,000 hours, and this is among the most stable perovskite silicon tandem. For this, we asked our some industry partner to design a very special stability testing unit for us. So for this individual unit, we can separately control the temperature, everything, and very precisely. So each cell have each temperature control and the light source, everything. Yeah, also very expensive. Yeah, but we can precisely monitor all the cells, and yeah, one by one. And okay, so I talk about perovskite. How much time? 10 minutes. Okay. I talk about the perovskite silicon tandem. People think about it's more for this utility scale solar farm, large applications. But there's also interesting application. Might be interesting for perovskite, especially at the early stage, because perovskite emerging technology. I don't believe this technology cannot be stable for 25 years at this stage. Yeah. So before we reach to 25 years, I mean, the cell may be stable for 10 years, stable for 5 years. And certainly there's some interesting application, which is okay. And if the lifetime is 5 years or 10 years. And so this includes a lot of integrate this PV, like the VI PV, and yeah, even satellite and some other indoor consumer electronics applications. Yeah, for those applications, actually, it has different requirements. Sometimes it's low weight, flexible, and efficiency like 25% is okay. Lifetime is less than 10 years. Yeah, and so we think about, okay, how we develop perovskite-based thin film tandem solar cells, and to make it potentially flexible and low weight. So if you look at this perovskite-based thin film technology, you can see there's different partners can make this thin film tandem with perovskite. So this is the cross-section of the perovskite CIGS. We're working on this, but if you look at the CIGS, it's very thick. It's about 2.2 micron. And this is a perovskite tandem, and yeah, Mercouri just mentioned. And this one, because we want to better enhance this near IR photons. So the trend right now is to make this thin light perovskite thicker and thicker to capture more photons. But this brings another challenge. You need to overcome the recombination, because diffusion length is longer, yeah? So you need to avoid recombination. But another one is perovskite OPV. So because organic has a very strong absorption coefficient at the near IR. So if we take this Y6 as an example, and it's not a good absorber in the visible. If you look at the absorption coefficient of this one, it's not very good. Yeah, but if you look at this near IR absorption coefficient, the Y6, this organic stuff is much better than all the other components. Yeah, so therefore this gives us an opportunity to make this bottom cell very thin. So it's about 100 nanometer. We can capture most of this red photons, and organic cell has a has an issue with stability. Everyone worry about that. And yeah, it's indeed, and especially the organic cell can degrade very fast under this UV light or the 100 photon. So what we see here with perovskite organic tandem, the perovskite basically filter out most of these 100 photons. The blue photons, green photons will absorbed by the perovskite. So perovskite acts as a filter, yeah? So all you have in the tandem is a near IR light on this organic solar cell. So with that, actually the OPV is, has a better stability, yeah. And yeah, so recently we also innovate this organic bottom cell, because the current organic bottom cell using Y6, the band gap is too wide. It's about 1.35 eV. If you look at this dual junction tandem SQ limit, the ideal band gap of the bottom cell should be around 1.0. Then you can really maximize the potential of the tandem. Otherwise, the bottom cell is too wide, you don't see too much advantages by making the tandem. You can just use a single junction, it's enough. So therefore, we need to think about to narrow the band gap of the OPV, and therefore the tandem start to be more efficient and start to make sense. So this is the control. If you look at this one, the band gap, as I said, is about 1.35. And what we did is, we did some innovations in this double bond. We introduced this double bond to this part. So actually, there's two opportunities to introduce double bond. One is here and one is here, and both, can narrow the band gap. And but this narrow too much. We upshape this HOMO level too much, so we don't have a driving force to dissociate these excitons. The host cannot transfer to here. Then actually we don't have a good performance device. In the end, we find the balance one is you have an asymmetry synthesis. So one double bond here, and there's no double bond. So we can upshape a little bit, but not too much, and then we can have a very good solar cell performance. So this is the GWAX, and all the other results show the morphology has no change. So we can maintain a good transportation. Yes, so this is the result, and if it's this P2EH1V, you can see we can dramatically enhance this near IR absorption. You can see the EQE response is quite clear, where it's become narrower. But if cannot become, it's difficult to become even narrower. And if with this one, the EQE actually drop immediately, because as I said, there's no driving force to extract the holes. So therefore, this whole EQE just collapses. You cannot get an efficient device. And in the end, this is the band gap. And we can tune the band gap from 1.35 to something around 1.27 to 6, getting close to this perovskite. And yeah, so this TA result also shows we need some driving force to separate the holes. Otherwise, we don't see the whole transfer from this non-fully accepted donor to the acceptor. Non-fully acceptor to the donor, yeah. And okay, so this is the solar cell performance. So it's about 27%. So for 1 square centimeter, certified 26%, and it's getting close to the perovskite tandem, but it's not still have a 1%, 2% gap. And in this paper, and quite recently, and not published yet, and recently in the lab, we also get even a better device, and we are certifying this one, and this efficiency around 30%, 1 square centimeter perovskite organic tandem, and it's married in-house. It's not certified yet, and we certified 2 months ago, and the result is about 29. It's not 30, 1% gap, and we want make it better. But even it's a 29 certified, I think it's quite close to the perovskite. Perovskite 1 square centimeter is also 29 something. Yeah. So I just want to say, and actually this technology, in terms of efficiency, can be close to the perovskite. Okay, and how much time I have? 3 minutes. Okay, I'll quickly go through this, and I talk about the efficiency. I talk about different tandem, but I didn't talk about if stability. I also talk about the vapor deposition. But how about the large scale? Can we go larger with this technology we see in the lab? And this is a recent collaboration with an industry partner. So what we did is we used the full vapor deposition of perovskite on this G12 half-cut wafer. This is the largest silicon wafer you can get from the market. So this is 210 mm. This is 105 mm. So this is the largest silicon wafer in the market. And with this one, certified QSS area is 29%. And the lab measurement is about 30%. So just demonstrate it's feasible and to go large scale. Yeah, this is also recent work, and it's a collaboration with our industry partner as well. And this is the solution process one, and the certified also G12 half cut is about 200 cm square, and this one is more than 32%. And then we further integrated with a big solar module. So this one is about 1.5 square meter big module, and so we are doing this outdoor testing, and yeah. Yeah, so this is outdoor stability, yeah. Yeah, I also, in Singapore, just maybe 1 minute, just quickly wrap up. And yeah, in Singapore, I also founded a company called Thin-Film Solar. And because I think that the Dean also mentioned this, not only the fundamental research, but people right now is also care about the commercialization. I just showcase some commercialization of the perovskite, yeah, in our company recently. The company founded in 2023, and yeah, actually last year we launched the largest production line in ASEAN area. So it's about 50 megawatt. And yeah, right now the company is about 40 people in Singapore. And yeah, so this is the factory. So we are working on this open stakes, 1.2 meter. And yeah, the factory clean room is 1,500. It's and that includes the office, and the other is about 2,500 square meter. And working on this a large wafer, large panel. Yeah, so previously we showed the record efficiency in the module. And right now we are commercializing this consumer electronics product. And the reason is there are two reasons. First one, the perovskite right now is, to be honest, is not 25 years stable. Yeah, so we don't want direct compete with the silicon in this utility scale market. Because in that market, there's two challenges. One is the cost. It's very cost sensitive. So we need to make sure everything is comparable to silicon. Yeah, we talk about 0.6 yuan per watt. Yeah, so that's very, very tough. And another one is for stability. And consumer electronics, we don't need to be 25 years stable. And many applications like the keyboard, this earbus, and others, this is around 3 years. For electronic shelf labels, it's like 7 years, 6 years. So I mean, perovskite, we can guarantee that stability. We already passed all this stability test. So we believe this more mature market to commercialize perovskite first. And yeah, so this our solar cell solutions. This is a performance. I just quickly go through this. And the stability, and yeah, and some applications, as you can see here, electronic shelf labels, so for the supermarket, and the CCTV, and the wireless, yeah, and charging, and trackers, and the keyboard. Keyboard, right now we are working with several very famous keyboard company, yeah, to develop this solar keyboard, and AI glasses, and yeah, remote control. And if you look at the Samsung TV, the remote, most of them is like a solar remote control, yeah. And also this is a tracker CO2 sensor. We have a customer in Japan, and we already deliver a lot of product to them. They install this like a smoke sensor on the ceiling. So they install them in this in Tokyo, Osaka. There's a hospital, school, office. They already use this one right now. And yeah, smart lock for the smart home, yeah. Okay, so yeah, quick acknowledgement of my group and my postdoc PD students, yeah, and the funding support from the Singapore government. Yeah, thank you very much.
Again, because of time issue, we would like to move to the next speaker, and then we have the final discussion with all panel team members. Okay, the next speaker, I guess, should suggest me to introduce her like that. So it's from the oldest university from Australia to the oldest university from Hong Kong. Let's welcome Professor Ho-Baillie. Sorry about that.
Hello, everybody. Yes, so I'm from University of Sydney, which is the oldest and hopefully the finest university in Australia. and I'm here in the oldest university of Hong Kong. And I realize you host from the oldest university in Singapore as well. So hopefully we're the finest researchers. I'm just joking. So this is a tandem solar cell turning a wind turbine in front of the Great Hall that they think is part of Harry Potter's Hogwarts. So thank you. So that's a laser pointer. There's no laser pointer. Don't worry about it. That's fine. Yeah. Okay, so at University of Sydney in our research group, we've got a program of work that's related to solar for space, which is my fellowship, to BIPV, which was an industry project a few years ago, for hydrogen 3 years ago, and lately we're doing sort of synaptic and for neuromorphic application. Okay, so moved from UNSW to Sydney in the last 5 years, and here are some of the work. Oh, thank you. All right, so I don't know how to do it with 2 hands, but we'll be fine. So yeah, so these are some of the work that is on PV, and we also look at metal halide perovskites for photodetectors, field effect transistors, and tandem solar cells for using 2-dimensional perovskite cell or layered perovskites for these applications. And the field effect transistors led to the synaptic device for neuromorphic application. Okay, so these are the very, very recent 2 papers in ACS Nano by Peter, who's in the audience, who did his master's at Hong Kong University, and also another work that we look at dark and bright excitons. Okay, so at University of Sydney, we are very fortunate to have some very bright undergraduate students who, if they're smart enough, they actually don't have to do the recipe-driven laboratory work. They can come and work with us for 6 months. And this is a great opportunity because we can do a lot of the blue sky research, non-funded research, and we can use those preliminary results to apply for more funding. So they're purely curiosity-driven, not milestone-driven, and therefore we're able to give the PhD students supervisory experience to supervise these really bright students. And because they're in a time constraint, they usually produce good work. So we supervised 63 students in the last 5 years. Don't know how we did it, but we did. And 11 of them contributed to 11 very good publications. So one of them is about the circularity work, which I will talk about shortly. But globally, how much photovoltaics do we need? Well, we need a lot. According to the International Renewable Energy Agency, we need around 14 terawatts of solar by 2050. But then if you look at another work published in Science, these people who are we've got PV background, they reckon we need 75 terawatts of PV. So that's a lot. That means we soon will be installing 1 terawatt of panels every year, which is possible because people in China are building terawatt scale factories and terawatt scale solar farms. And if you look at degradation rates in modules, you also look at early retirements, we may have to even install more terawatt or deploy more terawatt PV in the world. So the good thing with PV is it also enables developing countries. So these are photos, so that's me 25 years ago, where we took 15 undergraduate students to a very remote area in Nepal, and we install a very simple, very simple solar battery system to give them lighting. And then 1 year after, the students went back and installed another solar battery system to give them a fridge so that they can store their medicine. And that medical clinic served 30,000 people in the area. So you can see that solar does a really good work for developing nations, enabling literacy. They're able to read at night, which is very important. And but terawatt scale photovoltaics, what does it mean? It means a lot of metallurgical grade silicon, a lot of quartzite being purified. This process alone takes a week to do, and there's a lot of aluminium involved, glass involved, making those solar modules. So in terms of material, there's a high consumption. So Peter and I were curious to look at the circularity of PV. And we looked at the paper, and they're all about material circularity. So no one has looked at PV from the energy point of view. So we thought we'll give it a go, see what the conclusions will be. So we look at the target of 75 terawatts. We look at the three main incumbent silicon technology, PERC, TOPCon, and heterojunction, so version 1.1, 1.2, 1.3. And assuming this will be more efficient than that, that's more efficient than that. Every year the efficiency improves, and some people like to retire their module early, and some would like to have bifaciality, and some would like to recycle their modules. What happens? So the conclusions are different if you look at from the material perspective versus the energy perspective. So from the material perspective, it's actually encouraging lower efficiency modules if you can save materials. For example, if you can save glass or save the use of silver. Then they actually say it's okay to have even shorter lifetime modules. If you retire them early and recycle them, you can use the materials for the longer lifetime modules. But if you look at the silver point of view, then the conclusion is slightly different, and they say, well, go for the technology that uses less silver. But if you look at the energy point of view, the conclusion is saying, use the most efficient module, use them for as long as possible, and if you can do bifaciality, do that even if it means at the expense of extra piece of glass, because that's actually looking at using PV generated power to power the manufacturing of the next batch of solar panels. So, and other interesting findings from our work is the recycling, the benefit of recycling you don't see until a lot later, because we're deploying terawatts of modules and you're recycling maybe megawatts or gigawatts of modules, and it just puts a very, very small little dent in the recycling game. Okay, so it comes to the point of that's very important to have powerful modules, and because that will enable us to increase the circularity at the manufacturing and at the design stage of a product. And also, if we can have them last long, then we can also lengthen their lifetime cost, levelized cost of energy. Okay, so are the audience from PV background? So are you working on solar cells? Oh, okay, no. So, okay, well, why do we care about tandem? It's because the current technology, so I've got 20 minutes left, is that right? Okay, plenty of time. So the current technology silicon is based on one semiconductor material where it's got a fixed band gap, and therefore light with energy that is higher than the band gap. Not all of the energy got converted to electrical energy. So a lot of it just turned into heat. So you have very heat modules and not very efficient modules. Then you also have light with energy that is lower than the band gap. They don't get absorbed at all. So you have the sub-band gap loss, and then you have the thermalization loss. And therefore, the highest efficiency of the single junction is around 33%. Yeah? And also, people ask me, can you have 100% efficient module? Well, unfortunately not, because the solar cell is also an emitter, so you get the emission loss. You also get the emission angle loss, so there's a difference between the absorption angle and the emission angle. Then you have the entropy loss, and also there's heat flow, you know, from this hot sun to the cold environment, so you get that loss. So altogether, you don't quite get 100%. Anyhow, coming back to multi-junctions, so as you increase the number of junctions, you are putting material with high band gap. What it means is it converts all or most of the photon energy into electrical, and so you get a higher voltage, you add the voltage up, the current is the same, then you get 45% efficiency for two junction, 51% for triple junction, and so on. So as you can see, as you increase the number of junctions, you don't necessarily get a linear increase in efficiency. So you can see that people are stopping maybe at triple junction and quadruple junction for 3-5 materials. Okay, so what does it mean if we can really produce 40% efficient module by 2040. Well, that means we can accelerate the 75 terawatt target by 7 years. We can reduce the area required to deploy the 75 terawatts, and the area is equivalent to a country of Greece or England. So not United Kingdom, England. And we save a lot of glass and aluminium, and they're equivalent to multiple years of glass and aluminium consumptions, and lots of silver as well. So, the material that we're looking at is metal halide perovskites. So before they pop up, people who work on multi-junctional tandems are 3-5 people. They're in Japan, they're in America, they're in Europe, and nobody else could, because there are not that many experts in MOCVD and also MOPVE. But now lots of people working on tandem cells using metal halide perovskites. And as you can see, the data points get more and more crowded, and then in 2025, we just gave up. So there should be more data points, but we couldn't keep up. So now we just plot the highest efficiency data point. Now in 2020, it was a pivotal year, because that's when the perovskite OPV, perovskite 6, perovskite silicon tandem cell efficiency is higher than the single junction efficiency, record efficiency. So the year where triple junction will be higher, that will come soon. But as you can see, when you add another junction, you basically add another 5 more layers. So because you've got a positive, the hole selective layer, the electron selective layer, and then the positive electrode, negative electrode, that's 4 layers, and then you have the absorber 5 layers. So triple junction, essentially you got 15 layers that you have to worry about, and therefore it's not as easy as the double junction. But it's got the efficiency potential. So how do you build a tandem? You can grow, you can deposit the high bandgap material and low bandgap material, or you can just mechanically stack them so the electrical connection is independent, or you can divert the sunlight onto the high bandgap or the low bandgap. So that's okay for 2-junction, but as you move to triple junction, you can see that it gets more complicated, and we don't know or don't want to know how to do that in that configuration. So for triple junction, you get the 6-terminal, and monolithically, you still keep the 2-terminal configuration, which is quite elegant, and therefore our group has always concentrated on the monolithic tandem. Okay. So according to the industry roadmap, we're going to move from PERC to TOPCon to silicon heterojunction, and then even IBC, so have all the contacts at the back. So you look at the solar panels, it's all black. And also tandems probably coming in 2027, so they keep moving that year, pushing it a bit back because of the stability problem. And hopefully I'll touch on that. So in our group, we do the same thing. We have evolved from PERC to heterojunction. The quality of the figures improve, and we're also looking at from double junction to triple junction. So we also have moved from NIP to PIN, and I'll talk about why in the next slide, or the next slide after. So 2024, we were able to get our 1 square centimeter cell certified at 30%. So that year, at the same time, there are 7 groups who are able to do it. And by October, there are 10 groups, and then 1 year after, 25 groups. And I won't be surprised now, there may be 50 groups who are able to get 1 square centimeter perovskite silicon tandem cell certified at 30% efficient. Okay, so why do we move from NIP to PIN? It's because a lot of the whole transport layer is very absorptive. So absorb the sunlight, they steal the sunlight from the perovskite absorber, and it gets to nowhere. It doesn't get converted to electrical energy, and therefore we call it the parasitic absorption. So it's around 1.4 milliamps being lost there. Whereas if you look at the PIN, the N stack, they're all very thin and they don't absorb as much sunlight. So through that, we can gain 1.2 milliamps per square centimeter. So, and the other beautiful thing about PIN is people have been looking at using self-assembled monolayer to engineer the functionality of these layers for whole transport. So, this Guoliang is the very first student in our group who work on sort of engineering the whole transport layer. In this case, he added the benzene rings there so to delocalize the charges, and through that he could move the LUMO and the HOMO levels of the whole transport layer, and therefore improve the charge extraction. Also, the material is thermally stable and it improves the readability of the perovskite layer. So the perovskite layer is happy, and therefore there are fewer defects and much better interface. And through that, he was able to reduce the voltage loss in this high band gap material. And because it's thermally stable, we were able to get the cell to pass the IEC 61215 thermal cycling test. Okay, so the good thing is now you can buy this material. We didn't patent it, much to the disappointment of our university, but we feel like we're contributing to, you know, a little bit of changing the world through renewable energy development. Okay, so I don't have a lot of time left, so I won't touch on this work because I would like to talk about stability. So never mind, so this one is about the SAM layer where we engineered the pH of the precursor solution, and therefore we are able to stop the molecules from aggregating. And when you do that, you will get much better coverage. And we're able to do that by changing the pH to very low pH or very high pH to stop that aggregation and get very good coverage. And also this work, we're able to improve the stability of the tandem. So the one I show that what Guoliang produced was we were able to get the cells to pass the IEC 61215 thermal cycling test, which is 200 cycles. But in this case, we're able to get the cells to go through 1, 2, 3, 4, 5 times what the IEC requires, which is 1,000 thermal cycles. Also able to get the cell to pass another IEC test, which is the damp heat. So it's got the thermal cycling as well as the humidity. So how do we manage to do that is we have sort of years of experience about learning the degradation of perovskite in heat and moisture. So we build on the work that we did in 2020, where we had the very first GCMS study of perovskite degradation. So GCMS is known, you know, people use GCMS for all sorts of stuff, but no one sort of put the two to two together that you can use GCMS to study the degradation of perovskites. So why is GCMS good? Is because GC allows you to separate the products, and it's really good for mixed cation and mixed halide perovskites, yeah? So even back then, Mercouri was looking at mixing the lead and the tin, and there's also people mixing the halide, the iodine and the bromide into the perovskites. So we want to find out why the mixed ones are more stable and what happens if you mix the wrong species. So what we did was we used mass spectroscopy to identify the signature decomposition or outcasting products from the precursors. So we have the MAI, FAI, MABR, and then we also have the mixed perovskite precursors. We heat them at 85 degrees, 140 and 350, and then we look at the outgassing of those signature products from each. Okay, so I think the thing died, that's all right. Sorry about using the battery. So from the precursors. Okay, so then we used outgassing products to write a whole bunch of decomposition reactions. So you can see that CH3I is the main outgassing products from MAI, and then you have the HCN, the NH3 from the FAI. We also get the intermediate products of MAI, and these are not good because they actually further drive the decomposition reaction in equation 5. So, and these come out if you have the methylammonium. So having MA in even when you mix it with Fa, is not good because it drives the next decomposition reaction. So you can see that you will get the CH3I out of that when you have the mix MA, Fa perovskites. So if you just have Fa alone, you won't get that CH3I outgassing. Okay, so we also knew that MABR was more stable, looking at Professor Siok's solar cells, but here we can sort of confirm that using GCMS, where if you have MABR, it has a lower NH3 outgassing. So that's really good work. We also looked at what happens if you put cesium into cesium MA-Fa perovskites. And in fact, even if you have MA, in the presence of cesium, the outgassing is 5 times lower. Okay, so what does it mean in terms of encapsulating the cell? So then we looked at the 2 different schemes. So there are groups where they just put the PIB on the edge to stop the moisture ingress. But then you can also steal the idea from laminating 2 pieces of glass. You know, double glazing that is used in Europe, they laminate 2 pieces of glass. So it's like a blanket, so we call it a blanket. We compare the 2, and we also compare between PIB and POE in terms of the outgassing. We found that you need the blanket. You need the blanket to cover the perovskite so that you don't have the void for the outgassing to come out. So that stops the outgassing, and also we also look at the impact of the PIB, the difference between PIB and PO. So the conclusion is you need a polymer, you need glass, you need both of them, and you also need the blanketing to stop the thermal outgassing. And when you can suppress that, you can suppress the decomposition. And of course, the encapsulation also stops the moisture ingress. But this is a very nice piece of work because it's telling you there are 2 things that is happening to stabilize the solar cell. So now that work was looking at thermal stress on NIP, and now we're looking at heat and light stress and comparing between PIN and NIP cells. So what can we see here? Well, if you have heat and light, it makes the outgassing worse. But in this case, when you have heat and light, that outgassing is reduced. Why is it the case? It's because only in NIP, when you have the light stress, you have a whole bunch of other reactions that competes with this product. So they're actually competing. They're using that to drive other decomposition. And that doesn't happen in PIN. But thankfully, PIN cells is more stable than NIP, so you can see the outgassing here. So these are all PIN cells. They are a lot less than the NIP. So thank goodness for that. And people can also see that when they just look at the cell performance. Not shown here, but shown in the manuscript is in NIP cells, the heat drives the lead and iodide diffusions, whereas the light causes the lead zero defect at the interface. And it's really bad when you have the titanium dioxide compared to the tin oxide. So heat and light, when you combine them, yes, you get the synergistic degradation, but it's less so in PIN, especially if you're incorporating stabilizing active additives. So also, it is possible to make some perovskite cell more light stable. So what it means is, if you can manage the heat of the solar cell, if you can cool the solar cells down, and you can make the cell more light stable, it may be possible to improve the cell reliability, sort of to the extent of silicon. So through this knowledge, we apply it for tandem. So these are all the tandem cell and tandem module stability as measured against the IEC thermal cycling, humidity, freeze, and dam heat standard. And you can see, there are around 5 groups in the world that's just looking at tandem for passing IEC tests. Okay, so we also use that knowledge to look at triple junction. So this is the very first triple junction that passed an IEC test, and also we apply it for large areas. So at the time of reporting, that's the largest area cell, and therefore that's the most efficient large area triple junction. Okay, so that's something that if you're interested in looking at using different annealing process rather than hot plate processing for annealing perovskites, it's a lot shorter. We're using CO2 laser because it's a lot gentler on the perovskite bonds, and it enables localized patterning. And one thing we found that the substrate is a lot cooler if you use laser. And also we found that you don't see the phase segregation as you will see if it's hot plate anneal. We still don't quite understand why the phase segregation is suppressed in laser anneal process, but it could be because of the strain and in the film that is different when it's laser anneal. So we look at non-silicon perovskite tandem, and the reason is because they are very radiation tolerant in space. So all the thin film are a lot more radiation tolerant than silicon. We blast them with protons. We blast them so much that they become radioactive, and they're still very stable compared to silicon. And also they've got a shorter lifetime requirement, 5 years in space, and the only thing that we have to worry about is the temperature. So this is an undergraduate project where we were able to integrate the cells onto the printed circuit board, do all the electronics. We learn a lot. We learn a lot of non-solar stuff, and we were able to get them launched in 2024, and we occasionally get the data when the satellites wake up. So 2024, we also write an article. Peter and I wrote this review where we look at the thin film technology, and you can see some of the thin film technologies sort of coming back in terms of their potential for space. And I guess these two work I'm really proud of, because people talk about thin films, it gives you very good specific power, very high power to weight ratio. But one thing that people don't ignore is, okay, well, the solar cell sits on something, and that something can be heavy. So if the solar cell is sitting on printed circuit board, then it's actually not lightweight anymore, as opposed to maybe large array or roll-out solar array. Look at the reinforcement being used, look at even the glue being used. Then we sort of did a very good calculation looking at realistically what will be the real power to weight ratio. Also, people ask me about qualifications, so we look at the tests that are involved. And interestingly, some of the tests that are relevant to 3,5 cells are not relevant to perovskite cell, because perovskite cell is very different. It's a coating, and therefore it's not an individually freestanding cell where you interconnect. So some of the pool tests, some of the tests for 3,5 does not apply for perovskites. So we have to rethink how to test cells. But interestingly, with commercial space, people are internalizing the risk. So you have satellite integrators where they just buy off-the-shelf cells, and then they internalize the risk by just sending them up to space and hoping or praying or have some confidence that they will work. Okay, so another thing talked about is about flexible. So people thought about, flexible solar cells. Look at how wonderful I can bend it and this and that. But it's very different to wearables. So we actually don't need to worry about stretching, twisting, and crumbling. When they're in space, actually sitting on something that is rigid or semi-rigid, so they get folded out. So as long as the folding mechanism can survive that fatigue, we don't have to worry too much about these sort of stress. But we do need to look at the different other types of things, electronics, the printed circuit boards, and those development, which is more holistic than just the perovskite film itself. And of course, the high end-of-life power conversion efficiency is still extremely important, because we don't want to spend more stuff to space than what we required. There's already quite a lot of space debris. Okay, so last but not least, I'd just like to thank everybody, our group for doing the wonderful work, all the collaborators, and old friends, new friends that we meet always internationally. Thank you to those who have reviewed papers for ACS Nano. And we've got lots of submissions, but also the journal is very well received by readers, but also reviewers. So reviewers are very generous with their time. They always say yes. And the journal really cares about authors. I get pushed a lot every week that we have to look at papers quickly. So yes, so feel free to submit to this, and we'll do our best to get a very good review for you guys. So thanks very much.
Thank you, Professor Ho-Baillie. We will now take a tea break. This lecture will resume at 4:35 p.m. Enjoy your break and see you back here shortly. Yeah. Welcome back. We are excited to continue with the second part of the workshop and our upcoming panel discussion. Let's now hand the stage over to Professor Choy to introduce our next panelist.
Our next good friend is from City University of Hong Kong, Professor Zhang. I guess he's talking about something related to crystal, right? Let's welcome Professor Zhang.
Thank Professor Choy to invite me, and also it's also my great honor and a great pleasure to meet the Professor Professor Kanatzidis here. Actually, I feel a little bit nervous. Actually, I remember that 10 years ago I gave the seminar in the UK or in the USA, actually in the Boston College Golden Conference. That I will talk about the cation and also for the crystal glue. For the today's actually the topic is actually totally different from 10 years ago. For the today I'm going to talk about how to glue single crystal of the polymers and also the glue single crystal of the covalent organic frameworks. So one question is, why do we want to glue the single crystal of the polymers and covalent organic frameworks? So here actually in our daily life, we have a lot of polymers. Polymer can be divided two types. One is structural polymer, another actually is the functional polymer. Whatever in the lab, we can find the Teflon, right? And Teflon tab. And also in the supermarket, we can find a lot of the packaging, use plastic, and also our clothes actually is better use biopolymer. And that's on the top, actually is all these, sorry. How did it work? Okay. Maybe it doesn't work. Okay, it's okay. On the top, actually, on the top is a structural polymer, and then bottom is a functional polymer. Functional polymer actually a lot. For example, we have PSS polyidot. When we fabricate a device, for example, we fabricate the perovskite solar cell. Probably we use a PSS polyidot as a charge transfer layer to collect the charge and to transport charges. And also we have a lot of the polymer-based optical fiber, and also now the polymer have a lot of application in the flexible device. Now the question is, not all the polymer can meet our the requirement. So sometimes we need to do the modification for the polymers. So how? Now that we have a big issue. Big issue is what? When we try to introduce a functional group, whatever, or functional atom, and then where we put it, and also we don't know how the polymer chain stacking in the space. The reason is the knowledge about the polymer single crystal is much less, right? So here we have big challenge to glue the single crystal. The first thing is actually most of the polymer people reporting in the literature. The weight is actually the average weight. What's that mean? That means all the polymer synthesis, all the polymer synthesized by the people is a mixture because the polymer chain is not the uniform. So if you try to glue single crystal from the mixture, actually is very, very challenging. Sometimes is impossible. Okay, this is actually for the traditional polymer. Second, for the conjugated polymer, because the polymer chain is conjugated and the solubility is very, very poor. So if you try to glue the single crystal from the conjugated polymer, even worse. So in this case, we have to introduce a lot of the softer chain, try to increase solubility. However, softer chain, of course, affect the crystal glue. So even the system is very challenging to glue the single crystal, but in the literature, we do have a lot of ways to glue the single crystal. So my group actually gives some summary about the recent 2 years. You can see that starting from the 2010, and each year we do have the single crystal of the polymer reported in the literature. So my group gives a summary about this other single crystal, and then we know that they have 4 ways to glue the single crystal. The first way is direct glue. So what do you mean direct glue? We synthesize the polymer first, and then we dissolve all this polymer in the organic solvent, and then we try to evaporate, and then try to glue the single crystal. However, this method looks very, very simple, but it's very, very difficult. The reason when we synthesize this polymer, the polymer chain should be uniform. Otherwise, this polymer is a mixture, okay? The second method is topochemical polymerization. So this method requires that we need to make the polymer precursor first, and then we glue the single crystal of the precursor. And then this precursor can be converted the polymer crystal through the heating or through the light used or use pressure. So this pretty much based on the single crystal of the monomers to single crystal of the polymers by the the external stimulation. And then the third method is try to put the polymer chain into the inorganic matrix. So in this case, we know that inorganic matrix can easily to glue the single crystal. Actually, in Professor Mercouri's earlier job, Professor Mercouri done a lot of the research work, try to put the conjugated polymer chain in the inorganic matrix. And then, but at that time, I do believe Professor Mercouri didn't get any single crystal for the composite. So in my group, actually, when I was in the NTU, we developed the method, and then we found that we can integrating polymer into the inorganic matrix, and then we glue the single crystal, we solve the crystal structure, and then we can solve the polymer chain. And then I think this is the first time reporting the literature. And then in the literature till now, only 2 examples. And these 2 examples actually done by my group. One is I reporting the 2013, another reporting the 2015. Yeah. But this method is actually still very difficult. Okay. So now for today's talk, I'm going to talk about the talk about our method. Actually, this report is used by a lot of the group, and then is a very popular method. We try to use dynamic bonding to form the single crystal. The reason is when we glue the single crystal, and then the bonding arranged in the space maybe doesn't actually the perfect. So we need to the bonding dissociate again, and then reglue again. So this dynamic bonding actually is very, very important. In the literature, for example, we can use boron-nitrogen bonding. Also, we can use the imine bonding. And this is actually developed by the Professor Yagi, phosphate oxygen boron. And this 2 system, phosphate oxygen tellurium, boron oxygen tellurium, actually this is developed by my group. So later on, I will talk about the system. So the first, actually, we try to use the boron and the nitrogen bonding, this dynamic bonding to glue the single crystal of the polymers. Here, as we know that boron yeast, we do have this empty orbital. And then nitrogen, we do have the pair electrons. When these two species to meet each other, they can form the dative bonding. Actually, is coordinated covalent bonding. Okay, so this bonding energy is not that strong. So this can be dissociated, which can allow us to glue the single crystal of the polymers. So before my group working on this field, and several of the groups, for example, Jack here published one paper in Anguang Chemie in the 2023. He can make the single crystal of the polymers. And later on, Jack here and also write a very nice review in the Anguang Chemie in the 2023. So in China, also have the two very famous professors published the papers in this field. One professor actually is from the Fujian Normal University, Professor Zhang Jianjing, and then he published a lot of the research results. Another the professor is Professor Huang from Zhang University, and also work on this boron natural bonding, dative bonding to glue the single crystal. So you can look at here. Actually, before my group done this research, you can see a lot of the professors had already done this research. So what is our idea, right? So we should have different idea compared to the other groups. So when we look at all these building units carefully, we found out that all these building units actually almost have no function until this one. This actually is AIE molecules. So from here, so now my idea is it possible for us to use the organic semiconductor as a building unit, and then we connect together. They have the well ordered in the space, and then form array in the space, and then we should have more functions for our crystal. So based on these ideas, I asked my student Wang Xing. Now he had already got the PhD, and then he found the professor position in the Guizhou University, and then another postdoc, Dr. Zhang Li, work on this project. So we have here actually the tetrapyridine purfling, and also have the tetrapyridine TDF. We know that TDF actually is a very good connector, and then purfling can absorb the light. So initial idea actually we use the pyridine, this nitrogen, and from the coalition with the boron ester, they can form the two-dimensional or three-dimensional framework. Actually, when we control our experimental condition, we only found that whatever the tetraphenyl pyridine or this actually the TDF stuff, they only use the two pyridine to coordinate with the boron, and then leave other two pyridine dangling. So you can look at here. We get a very nice crystal as shown here. And then we solve the crystal structures. You can see that two pyridine dangling, whatever, in the TDF system or in the purfling system. And then these two pyridine connect this together. They form the linear structure as shown here. But one thing that I tell you guys, you look at this boron ester species, these two pyridine actually is cis structures, rather trans structure. Actually, this is very important. Why I mentioned this, later on our idea keep going, and then you will see this conformation change. Okay? Since we have TDF in our polymer, and then we want to look at the conductivity. Initially, we just take the single crystal, and then we look at the conductivity. You can see that almost insulate. And then after you use iodine doping, you can see the conductivity increase, become the semiconductor. Okay. And also, without doping, we do the photo conductivity. You can see almost have no photo current. However, if you shine with the light, you can see the conductivity will be increased. Okay, so when we finish this project, and then we are going to do even more. So what's going on here? So obviously, when we use the 4-pyridine direct connector TDF, and then this space is not good enough, so we can only use the 4-pyridine to connect the BACT. So it's possible for us to put the enlarge the space here. So the first try we use isoquinone as shown here. The second one, we put the one benzene ring between the TDF and also the piloting. And also we want to look at this piloting in the 4 position. Is it possible for us from 4 position to move the 3 position? And then what happened for this collaboration? So following this idea, and then we look at the very nice zinc crystal. This is initially commercially available, actually the 4 piloting TDF. You can see the BACT part, actually these 2 benzene ring. You can see actually they're in the trans structures rather than cis structures. However, when we change the piloting to the isoquinone, you can see that here still isoquinone. This actually space probably still not large enough, and then in this system, they only use the 2 isoquinone to do coordination. However, now you look at the BACD part. These 2 find actually is a cis configuration compared to here is a trans configuration. And then when we put the benzene in between the piloting and then TDF, you can see that, and then now the space is large enough, and then for piloting can do the coordination, and then we can get the nano load for the actually the polymer. And then we know that actually TDF itself is an electroactive sand, so we can use the TDF as the electrode for the rechargeable battery. And then here we use the sodium ion battery. You can see that actually the performance is very good. Okay. And then what happens if you move the nitrogen from the 4 position to 3 position? And what happens? And then it turns out the coordination will change, and then this can form the 2-dimensional structure as shown here. Okay. And then TDF actually is also very good as a catalytic sand. We can use this actually to the hydrogen peroxide evolution. So we just finished this result, and then this paper, we're still in preparation, and then hopefully we can submit this paper in the January, in the February. And then keep going. Now we use the TDF system. Now it's possible for us to extend our idea to some other system, right, besides the TDF. Okay, so another PhD student, the Zhang, now he has get a faculty position in the Shandong University, and also another actually joint PhD student between the CTU and then Central South University. Now she will get actually the PhD this year, and then she also get the faculty job in the Harbin, and after he get actually the PhD, I put here he moved to the Harbin, started his independent career. Okay. So here, why we want to use NDI? As we know that if you do the rechargeable battery, this is actually small molecule. If you use this as an electrode, and then if you do the cycle, this can only cycle maybe 2 to 3 times, and then the battery dead. Why something like that? Because this small molecule dissolve in the electrolyte. So in order to solve this issue, and then we use this our NDI to coordinate with our boron ester, we can get a very nice crystal, and then you solve it, this become polymer, and then solubility will drop a lot. So now we use this as a electrode, and then we do the rechargeable battery. You can see that the cycle we do the more than 120. Here I only see the 120. In our paper, we can cycle more than 20,000, and also this is different charges. Different charge current. Also, shows a very good performance for this actually the polymers. And then keep going. My postdoc, Dr. Zhang, and working another way. So it's possible for us to synthesize the 3 boron sand, and then we coordinate with the BYE, which is commercially available, and then we get a very nice crystal, and then we solve the crystal structure. You can see that the boron sand we have 2 coordinated. In the corner, we have the 3 coordinated. In the middle, we only have 2 coordinated. And then you look at the thickness of this nanobuild is 6 nanometer. Actually, to my understanding, use a single crystal to solve the crystal structure. I think this is the widest one. So since we have this material, and then what application for this material? We found that actually boron sand is a very good catalytic sand, and then in the dark, we cannot see any hydrogen evolution. However, when shine with light, and then you can see the hydrogen evolution. Okay. And then we use in situ hydrogen, and then to addition to the triple bond, you can see they always make the cis addition, and then the yield actually is very good. Whatever this benzene, we have electron donating or electron with the joint group, and then the yield is more than 90% and higher. And keep going. Actually, here is another postdoc, Dr. Halide. Actually, he did it this way. We try to have the more cooperation with the polymer chain, so that's why we use the sulfur and then 2 nitrogen here. So the first, when we get this crystal structures, and then he solved the crystal, and we found that these 2 nitrogen can coordinate with the boron sand, they can form the polymer chain, and then during the crystal glow, this polymer chain can intervene to each other from this chain, and then from the 2-dimensional. And these actually 2-dimensional structures intervene together. And then we can use this nanosheet to protect our lithium metal. So this actually have good application for the lithium metal battery to protect the metal. Okay. So keep going, and then my PhD student, Dr. Mr. Chen Zihao, to buy this actually commercial valuable compound, actually the spiral compound. We have the 4-pyridine here, and this 4-pyridine can coordinate with the BSCT, and then they can form the nanotube first. Organic nanotube, we can sampling from the 3-dimensional framework. In the inside, we do have the organic solvent. However, if we try to remove the organic solvent, and then this structure will collapse. So initially, we try to use this tube and then to do the separation. However, actually, we cannot keep the structure. So later on, actually, we still use this our material to the lithium metal protection, and it also turned out it actually works very well for the lithium-ion battery. And then what happened for the emission? So my another PhD student and postdoc, now he actually found the factory position in China. So what do we do actually? He make the 2 different actually the organic building unit. One is actually the 2-pyridine in the 3 and 6 position. Another is 2, 4, 7 position as shown here, and then 2, 7 as shown here, and then he glues the single crystal, and then for the 2 crystals, for the first one, you can see we have the very nice emission. However, for the second one, almost have no emission. Right? Since we have the crystal here, so it's easy for us to solve the crystal and then look at what's going on here. And then look at the crystal, you can see that for the 3-6 position, inside we have the solvent, and then these 2 polymer chain almost have no interaction to each other. However, for the bottom one, we do have, for the polymer chain, they have strong pi-pi interaction. So that bottom one, the emission will be quenched because of pi-pi stacking, but for the top one, they almost have no quench. They have the emission as shown here. So we also found that the organic solvent can replace by hexane, right? After by the hexane, you can see the emission is different. So we make this pattern here, and then, the right part, actually, we can use the hexane to do this change, and then under the 365 nanometer, we only see the green emission. However, if we use the 480 nanometer to shine, and then right part, you can also see the orange emission, okay, as shown here. So that is for the boron natural bonding. Actually, in my group, and also we try to introduce some the more strong bonding, which is also dynamic. Before my group actually conducted research, in the literature, you can see a lot of the strong dynamic bonding which is reported in the literature. For example, in the 2013, Weiss actually from Canada published a paper in the natural chemistry. They use the natural, actually NO bonding is the weak bonding. They can form a very nice crystal. And also the Professor Zhang from the Colorado, actually he published a paper in the natural chemistry. He used a polong nitrogen bonding. This also is a dynamic bonding. They can form the double helix structures. And this actually I have mentioned before. This is done by the Professor Yagi, and he uses the polong and oxygen and phosphate. They can form the cubic structure, and then cubic structure can be connected together by the benzene ring. They can form the three-dimensional structures. And this actually is very important for the curve structure. The first curve structures reported by the Professor Wang Wei from the London University. In the 2018, actually, he used from the imine bonding. For this single crystal glue, it takes about 1 month and 2 months. And then in the 2023, the same group published another paper in the Science. And then he put the strong acid inside and then can glue the curved crystal in 1 or 2 days. And then that's why he published another paper in the Science. In my group, is more interesting is tellurium stuff, because when I was in the Mercouri group, and then I also work on the tellurium stuff. So what we shown here, actually, these people reported here, actually, they use a tellurium oxide, which can self-sampling, they form the tellurium oxide chain. So from the idea here, so what I'm thinking is possible for us to use the diphenol tellurium oxide and then react with inorganic phosphate acid. Is it possible that works or not? If it works, and then we can change the inorganic phosphate to organic phosphate, we can make a lot of the curve or polymer or organic polymer structures. So my PhD student now, she had already got the PhD. She picked up this project, and then initially he uses the inorganic phosphate to react as a diphenyl ketone. And then it works very well. You can get a very nice crystal, and we solve the crystal structures. You can see they form the helix structure that was shown here. And then inside the chain is inorganic chain. We have the tellurium oxygen phosphate. Okay, and then since this chain is helix, so in the crystal we have the right-hand chain and also have the left-hand chain. And you can see the one layer is right hand and another layer is left hand. And then for the whole crystal in the space actually is non-symmetric. Okay, or is symmetric. Okay. So following this idea, you can see that it's possible for us to use the organic phosphate replace the inorganic phosphoric acid. Now it looks like it works very well. For example, we have commercially available 1,4-diphosphate phenol, and then, for example, the phenol can replace the naphthalene. Right? We can use the 135, or we can use the external, actually, the phosphoric acid. Okay. So now we can make the very nice crystal as shown here. For the first 3, we can make the 2D dimensional structures, and then for the third one, we can make the 3-dimensional frameworks. As we know that the tellurium is a very good catalytic center, so we can use our material to do this reaction. We have this amine here, and the amine can be oxidized, and then we have the imine structure as shown here. And then it looks, turns out actually the CD18 and the CD20 have very good performance, especially for the CD20 actually is a 3-dimensional framework. And then we use this actually as a catalyst, and then we do 4 cycles, and almost the conversion actually is 100%. Whatever the final group will have the electron donating or electron accepting, and then you can see the yield is more than 90% as shown here. And then what the mechanism actually is very simple. So we shine with the light, electron will excited from the Coulomb state to the excited state, and then the hole can oxidize amine. At the same time, the electron can reduce the oxygen, and then oxygen will reduce this amine again, become aldehyde, and react with the original amine in the system. They can become the imine structure as shown here. So this actually mechanism is the radical structures. Without a shine, and then in the whole material have no any radicals. However, shine with the light, you can see the radical as shown here. So besides the system, we also try to use the diphenyl tellurium oxide to react with the boronica acid. It looks like actually things works very well. And then we solve the crystal structures. Actually, this is a 3-dimensional framework, and then we do have a center here. Actually, this is a center. So we do the actually nonlinear optical property as shown here. You can see actually our material is very similar as the KDP commercial available. But one thing I have to point is that for the KDP actually is very sensitive to the moist, because KDP actually is the inorganic material, is inorganic salt. So in high moist system, KDP will have big trouble. So to my understanding, for this CD22 can replace the KDP in the high voltage system. Especially, for example, you can look at our UV absorption in the UV. Okay, so we can replace ADP for some KDP for some applications. Of course, now my group still continue working. It's possible for use organic polonic acid to replace the inorganic polonic acid, and then to do the crystal glue. We are still working, but our progress is a little bit slow as shown here. So now I give a summary. So why my group working on the single crystal of polymers? The first thing that we are going to realize is possible for us to realize the single crystal of the metallic or the conducting polymers. So if this can works, and then I'm pretty sure we can make the single crystal of the superconducting polymers. So we are still working. Actually, we're working very hard. Or hopefully we can, maybe in 2 to 5 years, we can report some result from my group about the superconducting polymer crystals or even metallic conducting polymers as shown here. Of course, actually, if we can finish these 2 projects, I'm pretty sure we can make the single crystal of the polymer-based topological insulate, and also can make the single crystal of the magnetic polymers. And cubic polymers, actually, we have already realized this, and then we will report our results soon about this part. For the emissive polymer, actually should be easy. Okay. So all the work is not done by me, it's done by group member. I like to thank all my group members for their hard working, and also I would like to thank a lot of professors to give me support. I like to thank them, and also I would like to thank the funding support from the Hong Kong government and also from the England government, and also I would like to thank you for your attention. Thank you.
I guess we just move to the last one.
I guess we can. Okay, thanks so much. Okay, guys, we take the last bit of time to share some of our results with you. This is Wallace Choy from EEE department to talk about the interfacial engineering issue for homogeneous and heterogeneous material system for the foldable devices. Perhaps not just perovskite, it's also foldable LED, organic-based infrared detector, as well as LED in our group. Some of the results that I actually asked some scientific questions during this day with Professor Kanatzidis for the core fundamental question. Here, I want to share with you how some of the material that we want to use in devices. So a lot of speakers talk about today, they showing very amazing performance that telling us that the PV generation coming, improving and improving. No matter what, mainly they talk about the rigid ways of the using the solar panel for electricity or power supply. There is a solar farm. But another degree of freedom, briefly mentioned by previous speaker, is the flexible devices. Indeed, if we open up the flexible devices, we can not just only the space. In daily life, they can open up a lot of applications. Again, not limited to perovskite devices. In some of our results we share with you, they can be for other devices for improving our quality of life by improving the device performance. So taking previous example with the flexible device that we can make them available for other applications, solar roof, bus, personal appliances, plus the cell phone, as you may know, that they are foldable nowadays. And yet, if we are talking about solution process, some of the speakers today, in order to improve the quality of perovskite, they do evaporation. But on the other hand, perovskite with most of the high-performance devices, they can also be fabricated by solution process. The solution process is another degree of freedom, advancing the technology. Flexible is one of them. Solution process, another degree of freedom is give us three low. Low cost, low carbon means a low carbon generation during the formations, and low power consumption, giving us truly easily achieving the carbon neutrality. So put it back to the flexible. We all know we always use ITO substrate, and then perhaps even if ITO. Actually, the cost of the perovskite is not much. You can ask a previous speaker. They can easily, so low, that's why we say low cost. They actually never, the ITO never will be low cost. It can only increase because of the limited source of the indium. And yet another killing issue is that not just the cost already killing, already 40 to 50% of the whole cost of the solution process devices. So no matter how high the performance they producing from perovskite devices, you have to pay another 40 to 50% for the substrate. And yet, this kind of ITO-based highly conductive electrodes, eventually they cannot be easily fabricated. Most of the time, you have to go for high power sputtering approach. And yet, they are actually, I don't have time to tell you more detail about ITO. Those ITO glass substrate that you get from the market, eventually it's not just by sputtering. You have to go for a number of processes before they can ship to you, mainly because they are sputtering crystalline properties make them actually, after fabrication, they are not very useful. They have to go through some other process. Nevertheless, therefore increase the cost. And also, because of high vacuum process, they cannot be easily compatible to the solution process to make the truly solution low-cost fabrication. And yet, just like you, how about the performance? The performance, the stability, all of them, if we compare to the rigid counterpart, all of them are issue. So starting from the substrate all the way to the flexible devices, the performance and stability, killing the issue of the hindering the application. So I guess the battery is some problem again. So anyway, so with that, we propose some replacement. We use what other people use. You can buy the silver nanowires. You can synthesize. You can just read papers as easily synthesize the metal oxide nanocrystals. Here, we introduce this tool by the simple solution process that we so-called ISPM method. We can have a tri-system integration of these two pieces of material. Why they are tri-system integration? Because we have silver wire, we have oxide nanocrystal. Each of them, they can integrate as a first case. And then the silver wire is the first case. You can see by our approach, you can see from the SEM, there's a surface of the silver wires. All of them, no matter you buy it or you synthesize by yourself, always have some insulative ligand protecting the nanowires. That's why they can be stable. Otherwise, they will aggregate, merge together, no longer be useful. Just like Chinese noodle at the very beginning. But with our approach, we can eliminate all the jacket, insulative jacket, and then promoting the coalescence of the silver nanowire at the joint. They atom are integrated together, no longer becomes individual wires. They becomes a silver net. So you can use it just like fishing, more stable and more conductive, number one. Number two, the oxide itself, they also, at the same time, during the synthesis, this is the second integration between the nanocrystal. The nanocrystal of the zinc oxide, this is example case, they will have a coalition themselves, making themselves as a cluster instead of small, tiny nanocrystal. So in this is a second integration happening during our process. Last but not the least, when the oxide close to the silver wire surface, the oxide themselves, take a look to this TM, they will deform themselves, spreading on the silver wire surface, forming atomically integrated structure. At that time, we haven't, most of the cases, we still see finally the lattice of the nanocrystal after forming this heterostructure structure, still zinc oxide. So without any artificial parameter, we found that this morphological change is just like a liquid-like behavior. So this plot of what we show here, showing us that eventually the old days that people found in some nanoparticles eventually can be used to explain our result that we are no longer just nanoparticle oxide. We are between oxide and silver wires, heterostructure structure, but the oxide eventually goes through the liquid-like behavior, forming the new species. And in our lab, we can synthesize different type of oxide, from N-type to P-type nanocrystal, such as P-type nickel oxide, people widely use it. And also we can tune the composition for different properties for the P and N. Then combined with the silver wire, we can form a series of electrodes. That's it useful. So we make comparison with what we make in our composite electrode. Again, our electrode is tri-integrated composite electrodes. So we try to benchmark ourselves, beating with ITO. So about our smoothness, we can make the electrode with smoothness less than 1 millimeter, roughness, peak to peak less than 4, the transparency over 88%, and the conductivity 7.5 ohm, which is pretty good compared to IDO. How about our stability? If you take a look at this diagram, we are under 85 humidity, 85 temperature degrees Celsius, and bending radius less than 1 millimeter, which is not bendable, eventually it's floatable. All the way old day is more than 10,000 times, now it's about 3,000 times, 30,000 times. We are very stable, under current, under humidity, under thermal. This is what the electrode will produce. The oxide wire composite that produced in the past, previous slide, here showing that it's potentially useful for devices as a transparent electrodes. Compared to the control, you can buy those ingredients, silver wire oxide mixed without our process. They will break down quickly. And the breakdown is interesting. You can see randomly they have a big jump. This big jump is because the silver wire, after during the operation, will heat up, and also during the bending, there's some stress. So they will break. And whenever silver wire break, you have a big drop of the conductivity. That's the reason they are not very durable compared to our device in terms of the stability. Nevertheless, compared to conventional, we are much thinner. As it depends on how you make it in lab, or you use some machine, just like Mayer rod. Then you can make it as thin as 5 micron in our lab. The weight is 1/7 of the total weight, so that we can make it truly light. And the cost is just 1/10 of the conventional. Make it potentially applicable. So this is a quick result. We make it, and then I'm not chemist, so I borrow the material from other group. They are good in making organic acceptor and donor for active layer material. So we borrow all the organic material. We try to show that with our electrode, we can make the performance good. In OPV, we are now about 20%, which is reasonably good in OPV field. And now the bending test telling you that we are foldable, not just flexible, with bending radius less than 1 millimeter. So now we start with a good point. We can make OPV as we showed you in last slide. How about perovskite? Perovskite is not just the flexible substrate or foldable substrate can make it foldable. The perovskite itself is a polycrystalline material, so it will crack when you bend it hardly. So we try to address the issue, and we first study the, let me see if I get you the old version. Indeed, this is the old version. Oh, apologize. Indeed, we address the stress in two ways. One is the delamination. Delamination, my team member already studied a new kind of sand material, have a strong interaction between the underneath structure and the perovskite, mounting the structure, helping to suppress the delamination of the layers. Because the PV device typically have a multiple layer from cathode, electron transport, it depends on what type of structure. If it is starting from anode, whole transporting layer, perovskite, electron transporting layer, and then cathode. That is a basic PIN structure, right? So each layer is different material. When you bend them, there are delamination. But I haven't shown you the slide there. Here, we address this by a new small molecule that can help to have a stronger bonding between the different layers, making them suppressing the delamination. Nevertheless, go back to the perovskite itself. Perovskite itself, you have a crack. So what we do is that we try to solve the problem of typical perovskite. We can see that typically, when we form perovskite film, this is a boundary between two grains of the perovskite. Eventually, this is STM. From the STM, you can extract the stress of the perovskite. We can find that from the top view, eventually stress created in these regions, okay? This is so-called, I just name it as a microscopic stress. On the other hand, because we are solution process, the composition cannot be exactly uniform from the bottom to the top in terms of the perovskite composition. So the change of the composition eventually create another stress. This is a macroscopic stress. So what we do is that we introduce some different small molecule in synthesizing the perovskite. It can help us to release the stress that we have originally in the control device. So in this device, we still have the grains, but we don't have a strong stress anymore. And also in the vertical directions, we find that from the XLD, we don't have any obvious pitch shift. Demonstrate that we release the stress and allow us to able to make perovskite solar cell this time with bending radius less than 0.75 millimeter. We are here. So we don't have any crack of the perovskite, nor the electrode. The electrode, we replace it by our composite oxide silver wires. So all the structure that we make is reasonably good for foldable device. So compared to the control, we take a look to the 5 millimeter flexible testing. Is already degraded. So we are about 1 order of magnitude better than the conventional. Not just the mechanical properties, eventually our operation stability also improved. Next, with this substrate, with the addressing the stress, we still want to address further issue that we have at the surface, at the boundary of the perovskite. Hopefully, even we have a good bulk perovskite, we still have the surface and boundary. They are the source of the defects, degrading the device performance as well as stability. So what we do is that we introduce the small molecule ED-MPT. This one, eventually, we are not just coating the small molecule on top to have a coating to suppress the defects. We actually would like those small molecule mounting the perovskite surface, making them become the corner share structure. We all know bulk inside this. The speaker previously mentioned good quality is a corner share crystalline, but the surface, because it's no longer the last layer, the crystal is not that perfect. What we do here is that we can allow the small molecule trying to maintain the corner share perovskite up to the top regions. favoring the stability of the perovskite, number one. Number two, we still address the defects. So all together allow us to, for the small area, 0.1 and slightly large area, 1 centimeter, the blue one is the control, our is the red, enhancing both the stability and the performance. So that is the cracking of cell, right? So next, we remember that we talk about we have surface, we have boundaries. Can we do something that we can not just look after the surface, we also look after the boundary? So what we do is that we try to find out some ligands which can add the modification which can help us to address both the boundary issue, that is the boundary, right, between the grains. That is the surface. Those two regions are where we have a lot of defects degrading the performance. So we introduce two groups of ligands, X and Y. X is targeted for the boundary, Y is targeted for the surface defects. So what we do is that we look like that most of these small molecules eventually help us to form the 2D material. So we are not coating an organic material just on top at the boundary. We are forming 2D material at the boundary as well as the surface. So what this is evidence that we indeed, when we introduce X, introduce Y, we can form the 2D materials. This makes us able to reasonably good performance without any encapsulation, because the 2D material form at the boundary, 2D material form at the surface, we make us able to sustain at 85% humidity, 85%, 85 degrees, 3,000 hours without encapsulation, very stable. Although our performance is not the world record in that device, but it works, demonstrate that the 2D material form at the boundary as well as the surface can help. So we claim we are at the boundary for the ligand X and helping addressing the boundary issue. And we also claim another ligand Y at the surface to address the surface issue. The molecule is so small, how can we measure it? How can we claim they truly help? So what we do is that we probe the AFM tip to the boundary region. This is boundary of the perovskite. This is a control. These are not very conductive because there are a lot of defects. But with our X, which we aim for boundary 2D formation perovskite, we can substantially improve the current. JV curve means eventually our X ligand do indeed go to the X boundary. How about the surface? If we just have the X ligand, they do not increase the conductivity of the surface. So it means the ligand of X do not help in the surface defects. How about the Y? The Y, we after boundary modification, we aim for surface, right? So here, showing us that Y do help the surface, increasing the conductivity of the surface by probing the AFM to the surface, and no change over the boundary. So we targetedly making the small molecule forming the 2D material at the targeted location, help us to address the boundary surface defects, suppressing the device. Next, we know the perovskite, we address the boundary, we address the surface. Another issue is that because we're a solution process, it's hard for us to maintain the cubic structure all the way when we form the perovskite. Because of solution process, we cannot absolutely. So always have the cubic and hexagonal structure forming all the time. So, but we know that the photo-absorbing material is the cubic perovskite. So what we do is that we try to introduce, later I realized, yesterday I visited Professor Zhang's group, we realized that at the time we believe this is a good choice, but it cannot dissolve in DMF. No way for us to help to incorporate the perovskite, making the perovskite more uniform. We cannot. So we introduced this urate to form the so-called eutectic molecules. This one can well disperse or dissolve in DMF, allow us to incorporate into the perovskite. Why we do so? Because with that hydrogen bonded eutectic molecules, it helps us to make the cubic one more energetical favor. So when we chemically do the solution process forming the crystal, it have more chance suppressing the hexagonal structure, enhance the crystal cubic structure formation. That is what we find out, that we finally favoring the perovskite forming more uniform in terms of the phase. We are more cubic phase. So with that, hopefully that we can work. Finally, this is our result showing us that we suppress the hexagonal phase and allow us to have more stable and more higher performance devices. So I guess people tell me, I skip this theoretical study. So nevertheless, we have bottom solution process, floatable device, we have the perovskite. Actually, we can use it for OPV and other organic devices as well. It works with that electrodes. And perovskite, we can address the boundary defects and make it flexible, floatable. How about the top electrode? People still suck into the high vacuum chamber for evaporation. Can we form the solution process electrode all the way from the scratch, without glass, by solution process at the last mile? We're still using solution process to finish the top electrode. We want to do so, but not easy because organic device, perovskite device is the solvent that we use as a top electrode solvent will easily attack all this organic and perovskite structure. So that's the reason evaporation is safe, because it don't have that problem. So we introduce this so-called dry non-immersive sintering strategy. Actually, what we do is that the sintering is by using the molecular beam boost. Actually, this one is what we, about 10 years ago, we introduced the molecular beam oxide by using this molecular beam boost to form the whole transporting material. But nevertheless, this one essentially helps us to provide us a protonation for the sintering. So this make the story short. We start with nanoparticles of silver. Eventually, in dry environment, the molecular beam boost help us to have the sintering of the silver nanoparticle becomes cluster. So the particle eventually they are not sintering at the beginning. The resistance is very high. After sintering, they become cluster. The conductivity is very good, and as good as what we can use in evaporated electrodes. We form it in solution process at room temperature. But you say, is this stable? If we scratch it, we peel off, we use a stick, a tape to stick it. This is a tape that we stick on the electrode. We cannot stick out the electrode. Means it quite strongly bond to the device without damaging the device. This is the OPV we demonstrated at that time by truly solution process top electrodes. So level N, we recently developed this metallic white electrode. Every morning when we wake up, we watch the mirror, see our face, right? Whether it's good shape or not. But the true reflection, if it is good, should be white color. This is the white color electrode that we make in our lab. Pure silver, 99.99, but it behaves white color, so it can reflect all light. So it is good for solar cell because if you cannot fully absorb in the first round of light get in, it totally reflect back for second trip. So you can have all the light will be absorbed again by your PV active layer. Number one, for LED, if it's for the back electrode, it can reflect all the light for light emitting from the top region. So we make it, and you can see, we start with nanocrystal or nanoparticle. At the end, it forms grains as what we can find in evaporated electrode. Eventually, if we evaporate silver, look at it in SEM, they are grains. So compared to the evaporated electrode, this is the solution process electrode, silver, metallic white silver electrode. The reflection is more than 90. The conductivity is here, pretty okay. For the evaporated electrode, they have a good reflection, but we are about there. But we have even better conduction than the evaporated, E stand for evaporated. So we are pretty okay. And finally, we make the OPV with reasonably good performance. So we make all solution process. Last but not the least is the foldable LED. We use the nanocrystal of perovskite. I don't have time to go through how we make the nanocrystal. We make the pale red, pale blue, and pale green nanocrystal. And now we make it floatable LED with our performance reasonably good. In terms of the EQE, this blue one is about 10%. The green one is about 28% EQE. And the bending radius is 1 millimeter, not bending, it's floatable. Over 3,000 times, it's still stable. So I guess with because of time, I guess I stop here. Not to read out what we talk about, but I guess thanks funding source and collaborators for their help, effort, and I end the talk with the picture of our university. Thanks a lot.
Thank